engine that rolls off the assembly line, and your new aircraft engine has some set of features X test. What the anomaly detection problem is, we want to know if this aircraft engine is anomalous in any way. In other words, we want to know if maybe this engine should undergo further testing, because or if it looks like an okay engine, and so it's okay to just ship it to a customer without further testing. So if your new aircraft engine looks like a point over there, well, that looks a lot like the aircraft engines we've seen before, and so maybe we'll say that it looks okay. Whereas if your new aircraft engine, if X test, were a point that were out here, so if X1 and X2 of the features of this new example, X test were all the way out there, then we would call that an anomaly, and maybe send that aircraft engine for further testing before we ship it to a customer, since it looks very different than the rest of the aircraft engines we've seen before. More formally, in the anomaly detection problem, we're given some data sets, x1 through xm of examples, and we usually assume that these m examples are normal or non-anomalous examples, and we want an algorithm to tell us if some new example, x test, is anomalous. The approach that we're going to take is that given this training set, given the unlabeled training set, we're going to build a model for P of x. In other words, we're going to build a model for the probability of x, where x are these features of, say, aircraft engines. And so, having built a model of the probability of x, we're then going to say that if for the new aircraft engine, if P of x test is less than some epsilon, then we flag this as an anomaly. So we see a new engine that has very low probability under our model P of x that we estimate from the data. Then we flag this anomaly. Whereas if P of x test is, say, greater than or equal to some small threshold, then we say that okay, it looks okay. And so given a training set like that plotted here, if you build a model, hopefully we'll find that aircraft engines, hopefully the model P of x will say that points that lie somewhere in the middle, that's pretty high probability, whereas points that are a little bit further out have lower probability, points that are even further out have somewhat lower probability, and a point that's way out here, a point that's way out there would be an anomaly. Whereas for a point that's way in there, right in the middle, this would be okay, because P of x right in the middle of that would be very high, because we've seen a lot of points in that region. Here are some examples of applications of anomaly detection. Perhaps the most common application of anomaly detection is actually fraud detection. If you have many users, and if each of your users take different activities, maybe on your website or in a physical plant or something, you can compute features, xi, of the different users' activities, and what you can do is build a model to say, what is the probability of different users behaving different ways? So what is the probability of a particular vector of features of a user's behavior? So, examples of features of a user's activity may be on the website. It'd be things like maybe x1 is how often does this user log in? X2 maybe the number of web pages visited or the number of transactions. Maybe x3 is the number of posts of the users on the forum. A feature x4 could be what is the typing speed of the user, and some websites can actually track that. So what's the typing speed of this user in characters per second? And so you can model P of x based on this sort of data. And finally, having modeled P of x, you can try to identify users that are behaving very strangely on your website by checking which ones have probability of x less than epsilon, and maybe send the profiles of those users for further review, or demand additional identification from those users or some such to guard against strange behavior or fraudulent behavior on your website. This sort of technique will tend to flag users that are behaving unusually, not just users that may be behaving fraudulently. So not just accounts that may have been stolen, or users that are trying to do funny things, or just find unusual users. But this is actually the technique that is used by many online websites that sell things to try to identify users behaving strangely, and that might be indicative of either fraudulent behavior or of accounts that have been stolen. Another example of anomaly detection is manufacturing. So I already talked about the aircraft engine thing, where we can find unusual, say, aircraft engines and send those for further review. A third application would be monitoring computers in a data center. I actually have some friends that work on this too. So if you have a lot of machines in a computer cluster or in a data center, you can do things like compute features of each machine. So maybe some features capturing how much memory used, number of disk accesses, CPU load, as well as more complex features like what is the CPU load on this machine divided by the amount of network traffic on this machine. Then given a data set of how your computers in your data center usually behave, you can model the probability of X. So you can model the probability of these machines having different amounts of memory use, or probably of these machines having different numbers of disk accesses or different CPU loads and so on. And if you ever have a machine whose probability of X, P of X is very small, then you know that machine is behaving unusually and maybe that machine is about to go down. You can flag that for review by a system administrator. And this is actually being used today by various data centers to watch out for unusual things happening on their machines. So that's anomaly detection. In the next video, I'll talk a bit about the Gaussian distribution and review properties of the Gaussian probability distribution. And in videos after that, we'll apply it to develop an anomaly detection algorithm. In this video, I'd like to talk about the Gaussian distribution, which is also called the normal distribution. In case you're already intimately familiar with the Gaussian distribution, it's probably okay to skip this video. But if you're not sure, or if it's been a while since you've worked with the Gaussian distribution or the normal distribution, then please do watch this video all the way to the end. And in the video after this, we'll start applying the Gaussian distribution to developing an anomaly detection algorithm. Let's say X is a real-valued random variable, so X is a real number. If the probability distribution of X is Gaussian with mean mu and variance sigma squared, then we'll write this as X, the random variable, tilde, that's this little tilde, read this is distributed as and then to denote the Gaussian distribution, sometimes when I write script n parentheses mu, comma, sigma squared. So this script n stands for normal, since Gaussian and normal distribution, they mean the same thing, so synonyms. And a Gaussian distribution is parameterized by two parameters, by a mean parameter, which we denote mu, and a variance parameter, which we denote by sigma squared. If we plot the Gaussian distribution, the Gaussian probability density, it'll look like the bell-shaped curve, which you may have seen before. And so this bell-shaped curve is parameterized by those two parameters, mu and sigma, and the location or the center of this bell-shaped curve is the mean mu, and the width of this bell-shaped curve, so roughly that, is the this parameter sigma. Is also called one standard deviation. And so this specifies the probability of X taking on different values. So X taking on values, in the middle here is pretty high, since the Gaussian density here is pretty high, whereas X taking on values further and further away will be diminishing in probability. Finally, just for completeness, let me write out the formula for the Gaussian distribution. So the probability of X, and I'll sometimes write this instead of P of X, I'm going to write this as P of X semicolon mu comma sigma squared. And so this denotes that the probability of X is parameterized by the two parameters mu and sigma squared. And the formula for the Gaussian density is this 1 over root 2 pi sigma e to the negative x minus mu squared over 2 sigma squared. So there's no need to memorize this formula. This is just the formula for the bell-shaped curve over here on the left. There's no need to memorize it, and if you ever need to use this, you can always look this up. And so that figure on the left, that is what you get if you take a fixed value of mu and take a fixed value of sigma, and you plot p of x. So this curve here, this is really p of x plotted as a function of x, for a fixed value of mu and of sigma squared. And by the way, sometimes it's easier to think in terms of sigma squared, that's called the variance, and sometimes it's easier to think in terms of sigma. So sigma is called the standard deviation, and it sort of specifies the width of this Gaussian probability density, whereas the square of sigma, so sigma squared, is called the variance. Let's look at some examples of what the Gaussian distribution looks like. If mu equals 0, sigma equals 1, then we have a Gaussian distribution that's centered around 0, because that's mu, and the width of this Gaussian, so that's one standard deviation, is sigma over there. Let's look at some examples of Gaussians. If mu is equal to 0 and sigma equals 1, then that corresponds to a Gaussian distribution that is centered at 0, since mu is 0, and the width of this Gaussian is governed or is controlled by sigma, by that variance parameter sigma. Here's another example. Let's say mu is equal to 0 and sigma is equal to 1/2. So the standard deviation is 1/2, and the variance sigma squared would therefore be the square of 0.5, would be 0.25. And in that case, the Gaussian distribution, the Gaussian probability density, looks like this. Is also centered at 0, but now the width of this is much smaller, because with smaller variance, the width of this Gaussian density is roughly half as wide. But because this is a probability distribution, the area under the curve, that is the shaded area there, that area must integrate to 1. This is a property of probability distributions. And so, this is a much taller Gaussian density because it's half as wide with half the standard deviation, but it's twice as tall. Another example, if sigma is equal to 2, then you get a much fatter, a much wider Gaussian density. And so here, the sigma parameter controls that this Gaussian density has a wider width. And once again, the area under the curve, that is the shaded area, it always integrates to 1. That's a property of probability distributions. And because it's wider, it's also half as tall in order to still integrate to the same thing. And finally, one last example would be if we now change the mu parameter as well, then instead of being centered at 0, we now have a Gaussian distribution that's centered at 3, because this shifts over the entire Gaussian distribution. Next, let's talk about the parameter estimation problem. So what's the parameter estimation problem? Let's say we have a data set of m examples, so x1 through xm, and let's say each of these examples is a row number. Here in the figure, I've plotted an example of a data set. So the horizontal axis is the x-axis, and I have a range of examples of x, and I've just plotted them on this figure here. And the parameter estimation problem is, let's say I suspect that these examples came from a Gaussian distribution. So let's say I suspect that each of my examples, xi, was distributed. That's what this tilde thing means. Let's say I suspect that each of these examples was distributed according to a normal distribution or a Gaussian distribution with some parameter mu and some parameter sigma squared. But I don't know what the values of these parameters are. The problem with parameter estimation is, given my data set, I want to try to figure out, or I want to estimate what are the values of mu and sigma squared. So if you're given a data set like this, it looks like maybe if I estimate what Gaussian distribution the data came from, maybe that might be roughly the Gaussian distribution it came from, with mu being the center of the distribution and sigma, the standard deviation, controlling the width of this Gaussian distribution. It seems like a reasonable fit to the data because it looks like the data has a very high probability of being in the central region, low probability of being further out, even low probability of being further out, and so on. So maybe this is a reasonable estimate of mu and sigma squared. That is, if it corresponds to a Gaussian distribution that looks like this. So what I'm going to do is just write out the formulas, the standard formulas for estimating the parameters mu and sigma squared. Our estimate, or the way we're going to estimate mu, is going to be just the average of my example. So mu is the mean parameter. Just take my training set, take my m examples and average them, and that gives me the center of this distribution. How about sigma squared? Well, the variance, I'll just write out the standard formula again. I'm going to estimate as sum over 1 through m of xi minus mu squared. And so this mu here is actually the mu that I compute over here using this formula. And what the variance is, or one interpretation of the variance, is that if you look at this term, that's the squared difference between the value I got in my example minus the mean, minus the center, minus the mean of the distribution. And so the variance I'm going to estimate as just the average of the squared differences between my examples minus the mean. And as a side comment, only for those of you that are experts in statistics, if you're an expert in statistics and if you've heard of maximum likelihood estimation, then these parameters, these estimates are actually the maximum likelihood estimates of the parameters mu and sigma squared. But if you haven't heard of that before, don't worry about it. All you need to know is that these are the two standard formulas for how you estimate, for how you try to figure out what are mu and sigma squared given the data set. Finally, one last side comment. Again, only for those of you that have maybe taken a statistics class before. But if you've taken a statistics class before, some of you may have seen the formula here where this is m minus 1 instead of m. So this first term becomes 1 over m minus 1 instead of 1 over m. In machine learning, people tend to use this 1 over m formula, but in practice, whether this is 1 over m or 1 over m minus 1, it makes essentially no difference, assuming m is reasonably large, you have a reasonably large training set size. So just in case you've seen this other version before, in either version works just about equally well, but in machine learning, most people tend to use 1 over m in this formula. And the two versions have slightly different theoretical properties. Their version works 1 over m minus 1. It makes essentially no difference, assuming m is reasonably large. People tend to use this 1 over n formula, but in practice, whether this is 1 over m or 1 over m minus 1, it makes essentially no difference, assuming m is reasonably large, you have a reasonably large training set size. So just in case you've seen this other version before, in either version works just about equally well, but in machine learning most people tend to use 1 over m in this formula. And the two versions have slightly different theoretical properties, slightly different mathematical properties, but in practice it really makes very little difference, if any. So hopefully you now have a good sense of what the Gaussian distribution looks like, as well as how to estimate the parameters mu and sigma squared of the Gaussian distribution if you're given a training set, that is, if you're given a set of data that you suspect comes from a Gaussian distribution with unknown parameters mu and sigma squared. In the next video, we'll start to take this and apply it to develop an anomaly detection algorithm. In the last video, we talked about the Gaussian distribution. In this video, let's apply that to develop an anomaly detection algorithm. Let's say that we have an unlabeled training set of m examples, and each of these examples is going to be a feature in Rn. So your training set could be m feature vectors from the last m aircraft engines that you manufactured, or it could be features from m users or something else. The way we're going to address anomaly detection is we're going to model P of x from this data set. So we'll try to figure out what are high probability features and what are low probability types of features. So x is a vector, and what we're going to do is model P of x as probability of x1, that is of the first component of x, times the probability of x2, so probability of the second feature, times the probability of the third feature, and so on, up to the probability of the final feature xn. I'm leaving space here because I'll fill in something remaining. So how do we model each of these terms, P of x1, P of x2, and so on? What we're going to do is assume that the feature x1 is distributed according to a Gaussian distribution with some mean, which we write as mu1, and some variance, which we write as sigma squared 1. And so P of x1 is going to be a Gaussian probability distribution with mean mu1 and variance sigma squared 1. And similarly, I'm going to assume that x2 is distributed Gaussian. That's what this little tilde stands for. That means distributed. It's distributed Gaussian with mean mu2 and sigma squared 2. So it's distributed according to a different Gaussian, which has a different set of parameters, mu2, sigma squared 2. And similarly, x3 is yet another Gaussian, and so this can have a different mean and a different standard deviation than the other features, and so on up to xn. And so that's my model. Just as a side comment for those of you that are experts in statistics, it turns out that this equation that I just wrote out actually corresponds to an independence assumption on the values of the features x1 through xn, but we're close to independence, and even if independence assumption doesn't hold true, this error works just fine. But in case you don't know those terms I just used, independence assumptions and so on, don't worry about it. You'll be able to understand and implement this algorithm just fine, and that comment was really meant only for the experts in statistics. And finally, in order to wrap this up, let me take this expression and write it a little bit more compactly. So I'm going to write this is a product from j equals 1 through n of P of xj parameterized by mu j comma sigma squared j. So this funny symbol here, this is actually a capital Greek alphabet pi, that funny symbol there corresponds to taking the product of a set of values. And so, you're familiar with the summation notation, so we write sum from I equals 1 through n, of I. This means 1 plus 2 plus 3 plus dot 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 up to n. Whereas this funny symbol here, this product symbol, right, product from I equals 1 through n of I, then this means that it's just like summation, except that we're now multiplying. So this becomes 1 times 2 times 3 times dot 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 up to n. And so using this product notation, this product from j equals 1 through n of this expression, that's just a more compact way, a shorter way of writing out this huge product of all of these terms up there. Since we're taking these P of xj given mu j comma sigma squared j terms and we're multiplying them together. And by the way, the problem of estimating this distribution P of x is sometimes called the problem of density estimation, so hence the title of the slide. So, putting everything together, here's our anomaly detection algorithm. The first step is to choose features or come up with features xi that we think might be indicative of anomalous examples. So what I mean by that is try to come up with features so that when there's an unusual user in your system that may be doing fraudulent things, or when, for the aircraft engine example, when there's something funny, something strange about one of the aircraft engines, choose features xi that you think might take on unusually large values or unusually small values for what an anomalous example might look like. But more generally, just try to choose features that describe what you think, that describe general properties of the things that you're collecting data on. Next, given a training set of m unlabeled examples, so x1 through xm, we then fit the parameters mu1 through mu_n and sigma squared 1 through sigma squared n. And so these were the formulas similar to the formulas we had in the previous video that we're going to use to estimate each of these parameters. And just to give some interpretation, mu j, that's my average value of the j feature, right? So mu j goes in this term p of xj, which is parameterized by mu j and sigma squared j. And so this says, for the mu j, just take the mean over my training set of the values of the j feature. And I just mentioned that you do this, you compute these formulas for j equals 1 through n. So you use these formulas to estimate mu1, to estimate mu2, and so on up to mu_n, and similarly for sigma squared. And it's also possible to come up with vectorized versions of these. So if you think of mu as a vector, so if mu is a vector, that's mu1, mu2, down to mu_n, then a vectorized version of that set of parameters can be written like so. Sum from I equals 1 through n, xi. And so this formula that I just wrote out estimates, where these xi are the feature vectors, this estimates mu for all the values of n simultaneously. And it's also possible to come up with a vectorized formula for estimating sigma squared j. Finally, when you're given a new example, so when you have a new aircraft engine and you want to know, is this aircraft engine anomalous? What we need to do is then compute p of x. What's the probability of this new example? So p of x is equal to this product, and what you implement, what you compute, is this formula, and we're over here. This thing here is just the formula for the Gaussian probability. So you compute this thing, and finally, if this probability is very small, you then flag this thing as an anomaly. Here's an example of an application of this method. Let's say we have this data set that I've plotted on the upper left of this slide. If you look at this, well, let's look at the features of x1. If you look at this data set, it looks like on average, the features x1 has a mean of about 5. And the standard deviation, if you look at just the x1 values of this data set, it has a standard deviation of maybe 2. So that's sigma 1. And looks like, the x2, the values of the features as measured on the vertical axis, it looks like that has an average value of about 3 and a standard deviation of 1. So if you take this data set and if you estimate, mu1, mu2, sigma 1, sigma 2, this is what you get. And again, I'm writing sigma here, thinking of standard deviations, but the formula on the previous slide actually gave estimates for the squares of these things. So sigma squared 1 and sigma squared 2. So just be careful whether you're using sigma 1, sigma 2, or sigma squared 1 or sigma squared 2. So sigma squared 1, of course, would be equal to 4, for example. It's the square of 2. And in pictures, what p of x1 parameterized by mu1 and sigma squared 1, and p of x2 parameterized by mu2 and sigma squared 2, that would look like these two distributions over here. And it turns out that if you were to plot p of x, right, which is the product of these two things, you can actually get a surface plot that looks like this. So this is a plot of p of x where the height above this, where the height of this surface at a particular point, so given a particular x1, x2 values, so if x1 equals 2, x equals 2, that's this point, and the height of this 3D surface here, that's p of x. So p of x, that is the height of this plot. This is literally just p of x1 parameterized by mu1, sigma squared 1, times p of x2 parameterized by mu2 second squared 2. Now, so this is how we fit the parameters to this data. Let's say we have a couple new examples. Maybe I have a new example there. Is this an anomaly or not? Or maybe I have a different example. Maybe I have a second example over there. So is that an anomaly or not? The way we do that is we would set some value for epsilon. Let's say I've chosen epsilon equals 0.02. I'll say later how we choose epsilon. But let's take this first example. Let me call this example x1 test. And let me call the second example x2 test. What we do is we then compute p of x1 test. So we use this formula to compute it, and this looks like a pretty large value. In particular, this is greater than or equal to epsilon, and so there's a pretty high probability, at least bigger than epsilon, so we'll say that x1 test is not an anomaly. Whereas if you compute p of x2 test, well, that's just a much smaller value, so this is less than epsilon, and so we'll say that that is indeed an anomaly because it's much smaller than that epsilon that we chose. And in fact, I didn't prove it here. What this is really saying is that if you look at this 3D surface plot, is saying that all the values of x1 and x2 that have a high height above the surface corresponds to a non-anomalous, or sort of an okay or normal example, whereas all the points far out here, all the points out here, all those points have very low probability, and so we're going to flag those points as anomalous, and so it's going to define some region that maybe looks like this, so that everything outside this it flags as anomalous, whereas the things inside this ellipse I just drew, if it considers okay or non-anomalous, not anomalous examples. And so this example, x2 test, lies outside that region, so it has very small probability, and so we consider it an anomalous example. In this video, we talked about how to estimate p of x, the probability of x, for the purpose of developing an anomaly detection algorithm. And define some region, test. What we do is we then compute epsilon. Let's say I've chosen epsilon equals 0.02. I'll say later how we choose epsilon. But let's take this first example. Let me call this example x1 test. And let me call the second example x2 test. What we do is we then compute p of x1 test. So we use this formula to compute it, and this looks like a pretty large value. In particular, this is greater than equal to epsilon, and so there's a pretty high probability, at least bigger than epsilon, so we'll say that x1 test is not an anomaly. Whereas if you compute p of x2 test, well, that's just a much smaller value, so this is less than epsilon, and so we'll say that that is indeed an anomaly because it's much smaller than that epsilon that we chose. And in fact, I didn't prove it here. What this is really saying is that if you look at this 3D surface plot, it's saying that all the values of x1 and x2 that have a high height above the surface corresponds to a non-anomalous, or sort of an okay or normal example, whereas all the points far out here, all the points out here, all those points have very low probability, and so we're going to flag those points as anomalous, and so it's going to define some region that maybe looks like this, so that everything outside this it flags as anomalous, whereas the things inside this ellipse I just drew, if it considers okay or non-anomalous, not anomalous example. And so this example, x2 test, lies outside that region, so it has very small probability, and so we consider it an anomalous example. In this video, we talked about how to estimate p of x, the probability of x, okay or non-anomalous, not anomalous. Whereas the things inside this ellipse I just drew, if it considers okay or non-anomalous. Probability of x for the purpose of developing an anomaly. In the last video, we developed an anomaly detection algorithm. In this video, I'd like to talk about the process of how to go about developing a specific application of anomaly detection to a problem. And in particular, this will focus on the problem of how to evaluate an anomaly detection algorithm. In previous videos, we'd already talked about the importance of row number evaluation, and this captures the idea that when you're trying to develop a learning algorithm for a specific application, you need to often make a lot of choices, like choosing what features to use and so on. And making decisions about all of these choices is often much easier if you have a way to evaluate your learning algorithm that just gives you back a number. So if you're trying to decide, I have an idea for one extra feature, do I include this feature or not? If you can run the algorithm with the feature and run the algorithm without the feature, and just get back a number that tells you, did it improve or worsen performance to add this feature, then it gives you a much better way, a much simpler way with which to decide whether or not to include that feature. So in order to be able to develop an anomaly detection system quickly, it's really helpful to have a way of evaluating an anomaly detection system. In order to do this, in order to evaluate an anomaly detection system, we're actually going to assume that we have some labeled data. So far we'll be treating anomaly detection as an unsupervised learning problem using unlabeled data. But if you have some labeled data that specifies what are some anomalous examples and what are some non-anomalous examples, then this is how we actually think of as the standard way of evaluating an anomaly detection algorithm. So taking the aircraft engine example again, let's say that you have some labeled data of a lot of just a few anomalous examples of some aircraft engines that were manufactured in the past that turned out to be anomalous, it turned out to be flawed or strange in some way. And let's say we also have some non-anomalous examples, so some perfectly okay examples. So I'm going to use y equals 0 to denote the normal or the non-anomalous examples, and y equals 1 to denote the anomalous examples. The process of developing and evaluating an anomaly detection algorithm is as follows. We're going to think of as the training set, and talk about the cross-validation and test sets later, but the training set, we usually think of this as still the unlabeled training set. And so this is our large collection of normal, non-anomalous, and not anomalous examples. And usually we think of this as being non-anomalous, but it's actually okay even if a few anomalies slip into your unlabeled training set. And next we're going to define a cross-validation set and a test set with which to evaluate a particular anomaly detection algorithm. So specifically for both the cross-validation and test sets, we're going to assume that we can include a few examples in the cross-validation set and the test set that contain examples that are known to be anomalous. So the test set, say, will have a few examples with y equals 1 that correspond to anomalous aircraft engines. So here's a specific example. Let's say that altogether, this is the data that we have. We have manufactured 10,000 examples of engines that, as far as we know, were perfectly normal, perfectly good aircraft engines. And again, it turns out to be okay, even if a few flawed engines slips into this set of 10,000 is actually okay. But we kind of assume that the vast majority of these 10,000 examples are good, normal, non-anomalous engines. And let's say that historically, in however long we've been running our manufacturing plant, let's say that we end up getting 20 flawed or 20 anomalous engines as well. And for a pretty typical application of anomaly detection, the number of known anomalous examples, that is with y equals 1, we may have anywhere from 20 to 50 would be a pretty typical range of examples, number of examples that we have with y equals 1. And usually we'll have a much larger number of good examples. So given this data set, a fairly typical way to split it into the training set, cross-validation set, and test set would be as follows. Let's take our 10,000 good aircraft engines and put 6,000 of that into the unlabeled training set. So I'm calling this an unlabeled training set, but all of these examples are really ones that correspond to y equals 0 as far as we know. And so we will use this to fit P of x, right? So we will use these 6,000 engines to fit P of x, which was that P of x1 parameterized by mu1 sigma squared 1 up to P of xn parameterized by mu n sigma squared n. And so it would be these 6,000 examples that we would use to estimate the parameters mu1 sigma squared 1 up to mu n sigma squared n. So that's our training set of all good, or the vast majority of good examples. Next, we will take our good aircraft engines and put some number of them in the cross-validation set, put some number of them in the test set. So 6,000 plus 2,000 plus 2,000, that's how we split up our 10,000 good aircraft engines. And then we also have 20 flawed aircraft engines, and we'll take that and maybe split it up, put 10 of them in the cross-validation set and put 10 of them in the test set. And in the next slide, we'll talk about how to actually use this to evaluate the anomaly detection algorithm. So what I've just described here is probably the recommended or pretty good way of splitting the labeled and unlabeled example, the good and the flawed aircraft engines, where we use like a 60-20-20% split for the good engines, and we take the flawed engines and we put them just in the cross-validation set and just in the test set. And we'll see in the next slide why that's the case. Just as an aside, if you look at how people apply anomaly detection algorithms, sometimes you see other people split the data differently as well. So another alternative, this is really not a recommended alternative, but some people will take of your 10,000 good engines, maybe put 6,000 of them in the training set, and then put the same 4,000 in the cross-validation set in the test set. And so, we like to think of the cross-validation set and the test set as being completely different data sets than each other. But in anomaly detection, for sometimes you see people sort of use the same set of good engines in the cross-validation set and the test sets, and sometimes you see people use exactly the same set of anomalous engines in the cross-validation set and the test set. And so all of these are considered less good practices and definitely less recommended. Certainly, right, using the same data in the cross-validation set and the test set, that's sort of not considered good machine learning practice. But sometimes you see people do this too. So, given the training, cross-validation, and test sets, here's how you evaluate, or here's how you develop and evaluate an algorithm. First, we take the training set and we fit the model P of x, so we fit all those Gaussians to my m unlabeled examples of aircraft engines, and these are, I'm calling them unlabeled examples, but these are really examples that we're assuming are good or the normal aircraft engines. Then, imagine that your anomaly detection algorithm is actually making predictions. So on the cross-validation of the test set, given a, say, test example x, think of the algorithm as predicting that y is equal to 1, if p of x is less than epsilon, it's predicting 0 if p of x is greater than or equal to epsilon. So it's trying to predict, given x, it's trying to predict what is the label. Is it y equals 1 corresponding to an anomaly, or is it y equals 0 corresponding to a normal example? So given the training, cross-validation, and test sets, how do you develop an algorithm, and more specifically, how do you evaluate an anomaly detection algorithm? Well, to do so, the first step is to take the unlabeled training set and to fit the model P of x to the training data. So you take this, I'm calling it unlabeled training set, but really these are examples that we're assuming the vast majority of which are normal aircraft engines, not anomalies, and we're going to fit the model P of x. So we'll fit all those parameters for all the Gaussians on this data. Next, on the cross-validation of the test set, we're going to think of the anomaly detection algorithm as trying to predict the value of y. So in each of my, say, test examples, we have these xi tests, yi tests, where y is going to be equal to 1 or 0, depending on whether this was an anomalous example. So given input x in my test set, my anomaly detection algorithm, think of that as predicting that y is 1, if p of x is less than epsilon, so predicting that is an anomaly, the probability is very low. And we think of the algorithm as predicting that y is equal to 0 if p of x is greater than or equal to epsilon, so predicting that it's a normal example if the p of x is reasonably large. And so we can now think of the anomaly detection algorithm as making predictions for what are the values of these y labels in the test sets or in the cross-validation set. And this puts us somewhat more similar to the supervised learning setting, right, where we have like a label test set and our algorithm that's making predictions on these labels, and so we can evaluate it by seeing how often it gets these labels right. Of course, these labels will be very skewed because y equals 0, that is normal examples, will usually be much more common than y equals 1, than anomalous examples, but this is much closer to the sorts of evaluation metrics we can use in supervised learning. So what's a good evaluation metric to use? Well, because the data, because the data is very skewed, because y equals 0 is much more common, classification accuracy would not be a good evaluation metric. So we talked about this in the earlier video. If you have a very skewed data set, then predicting y equals 0 all the time will have very high classification accuracy. Instead, we should use evaluation metrics like computing the fraction of true positives, false negatives, true negatives, compute things like that, or compute the precision and recall of this algorithm, or do things like compute the F1 score, right, which is a single row number way of summarizing the precision and the recall numbers. And so these would be ways to evaluate an anomaly detection algorithm on your cross-validation set or on your test set. Finally, earlier in the anomaly detection algorithm, we also had this parameter epsilon, right? So epsilon was this threshold that we would use to decide when to flag something as an anomaly. And so if you have a cross-validation set, another way, one way to choose this parameter epsilon would be to try many different values of epsilon, and then pick the value of epsilon that, let's say, maximizes F1 score, or that otherwise does well on your cross-validation set. And more generally, the way to use the training, testing, and cross-validation sets is that when we're trying to make decisions like what features to include, or trying to tune the parameter epsilon, we would then continually evaluate the algorithm on the cross-validation set. So we make all those decisions like what features to use, how to set epsilon, use that, evaluate the algorithm on the cross-validation set, and then when we've picked a set of features, when we've found the value of epsilon that we're happy with, we can then take the final model and evaluate it, do the final evaluation of the algorithm on the test set. So in this video, we talked about the process of how to evaluate an anomaly detection algorithm. And again, being able to evaluate an algorithm with a single row number evaluation, with a number like an F1 score, that often allows you to make much more efficient use of your time when you're trying to develop an anomaly detection. In the last video, we talked about the process of evaluating an anomaly detection algorithm, and there we started to use some label data with examples that we knew were either anomalous or not anomalous, with y equals 1 or y equals 0. And so the question then arises of, if we have this label data, if we have some examples that are known to be anomalies and some that are known not to be anomalies, why don't we just use a supervised learning algorithm? So why don't we just use logistic regression or a neural network to try to learn directly from our labeled data to predict whether y equals 1 or y equals 0. In this video, I'll try to share with you some of the thinking and some guidelines for when you should probably use an anomaly detection algorithm and when it might be more fruitful to consider using a supervised learning algorithm. This slide shows what are the settings under which you should maybe use anomaly detection versus when supervised learning might be more fruitful. If you have a problem with a very small number of positive examples, and remember, examples of y equals 1 are the anomalous examples, then you might consider using an anomaly detection algorithm instead. So having 0 to 20, maybe up to 50 positive examples might be pretty typical. And usually we have such a small positive set of positive examples, we're going to save the positive examples just for the cross-validation set and the test set. And in contrast, in a typical normal anomaly detection setting, we will often have a relatively large number of negative examples of the normal examples of normal aircraft engines, and we can then use this very large number of negative examples with which to fit the model P of X. And so this is the idea that in many anomaly detection applications, you have very few positive examples and lots of negative examples, and when we're doing the process of estimating P of X, of fitting all those Gaussian parameters, we need only negative examples to do that. So if you have a lot of negative data, we can still fit P of X pretty well. In contrast, for supervised learning, more typically we would have a reasonably large number of both positive and negative examples. And so this is one way to look at your problem and decide if you should use an anomaly detection algorithm or a supervised learning algorithm. Here's another way that people often think about anomaly detection algorithms. So for anomaly detection applications, often there are many different types of anomalies. So think about aircraft engines. There are so many different ways for aircraft engines to go wrong, right? There's so many things that could go wrong that could break in an aircraft engine. And so if that's the case, and if you have a pretty small set of positive examples, then it can be hard for an algorithm, difficult for an algorithm, to learn from your small set of positive examples what the anomalies look like. And in particular, future anomalies may look nothing like the ones you've seen so far. So maybe in your set of positive examples, maybe you've seen 5 or 10 or 20 different ways that an aircraft engine could go wrong. But maybe tomorrow you need to detect a totally new set, a totally new type of anomaly, a totally new way for an aircraft engine to be broken that you've just never seen before. And if that's the case, then it might be more promising to just model the negative examples with this sort of a Gaussian model P of X, rather than try too hard to model the positive examples, because tomorrow's anomaly may be nothing like the ones you've seen so far. In contrast, in some other problems, you have enough positive examples for an algorithm to get a sense of what the positive examples are like. And in particular, if you think that future positive examples are likely to be similar to ones in the training set, then in that setting, it might be more reasonable to have a supervised learning algorithm that looks at a lot of positive examples, looks at a lot of negative examples, and uses that to try to distinguish between positives and negatives. So hopefully this gives you a sense of, if you have a specific problem, should you think about using an anomaly detection algorithm or a supervised learning algorithm. And the key difference really is that in anomaly detection, often we have such a small number of positive examples that it's not possible for a learning algorithm to learn that much from the positive examples. And so what we do instead is take a large set of negative examples and have it just learn a lot, learn P of X from just the negative examples of the normal aircraft engine, say, and we reserve the small number of positive examples for evaluating our algorithm to use in either the cross-validation set or the test set. And just as a side comment about this many different types of anomalies, in some earlier videos we talked about the email spam examples. In those examples, there are actually many different types of spam email, right? The spam email is trying to sell you things, spam email trying to steal your passwords, it's called phishing emails, and many different types of spam emails. But for the spam problem, we usually have enough examples of spam email to see, most of these different types of spam email, because we have a large set of examples of spam, and that's why we usually think of spam as a supervised learning setting, even though there are many different types of spam. And so if we look at some applications of anomaly detection versus supervised learning, we'll find that in fraud detection, if you have many different types of ways for people to try to commit fraud and a relatively small training set, a small number of fraudulent users on your website, do not use an anomaly detection algorithm. I should say, if you're a very major online retailer, and if you actually have had a lot of people try to commit fraud on your website, so you actually have a lot of examples with y=1, then sometimes fraud detection could actually shift over to the supervised learning column. But if you haven't seen that many examples of users doing strange things on your website, then more frequently fraud detection is actually treated as an anomaly detection algorithm rather than with a supervised learning algorithm. Other examples, we talked about manufacturing already, is doing strange things on your website, then more frequently fraud detection is actually treated as an anomaly detection algorithm rather than with a supervised learning algorithm. Other examples, we talked about manufacturing already. Hopefully you've seen more normal examples and not that many anomalies. But if again, for some manufacturing processes, if you're manufacturing very large volumes and you've seen a lot of bad examples, maybe manufacturing could shift to the supervised learning column as well. But if you haven't seen that many bad examples of your own products, then I do this anomaly detection. Monitoring machines in the data center, again, similar sorts of arguments apply. Whereas email spam classification, weather prediction, and classifying cancers, if you have equal numbers of positive and negative examples, or if you have many examples of your positive and your negative examples, then we would tend to treat all of these as supervised learning problems. So hopefully that gives you a sense of what are the properties of a learning problem that would cause you to treat it as an anomaly detection problem versus a supervised learning problem. And for many of the problems that are faced by various technology companies and so on, we actually are in these settings where we have very few or sometimes zero positive training examples. Maybe there's so many different types of anomalies, we've never seen them before. And for those sorts of problems, very often the algorithm that is used is an anomaly detection algorithm. By now you've seen the anomaly detection algorithm, and we've also talked about how to evaluate an anomaly detection algorithm. Turns out that when you're applying anomaly detection, one of the things that has a huge effect on how well it does is what features you use or what features you choose to give the anomaly detection algorithm. So in this video, what I'd like to do is say a few words, give some suggestions and guidelines for how to go about designing or selecting features to give to your anomaly detection algorithm. In our anomaly detection algorithm, one of the things we did was model the features using this sort of Gaussian distribution with xi, mu I, comma, sigma squared I, let's say. And so one of the things I often do will be to plot the data or plot a histogram of the data to make sure that the data actually looks vaguely Gaussian before feeding it to my anomaly detection algorithm. And it will usually work okay even if your data isn't Gaussian, but it's sort of a nice sanity check to run. And by the way, in case the data looks non-Gaussian, the algorithm will often work just fine. But concretely, if I plot the data like this, and it looks like a histogram like this, and the way to plot a histogram is to use the HIST or the HIST command in Octave. But it looks like this. This looks vaguely Gaussian, so if my features look like this, I'd be pretty happy feeding it to my algorithm. But if I were to plot a histogram of my data, and if it were to look like this, well, this doesn't look at all like a bell-shaped curve, right? This is a very asymmetric distribution. It has a peak way off to one side. If this is what my data looks like, what I'll often do is play with different transformations of the data in order to make it look more Gaussian. And again, the algorithm will usually work okay even if you don't, but if you use these transformations to make your data more Gaussian, it might work a bit better. So given a data set that looks like this, what I might do is say take a log transformation of the data And if I do that and replot the histogram, what I end up with in this particular example is a histogram that looks like this. And this looks much more Gaussian, right? This looks much more like the classic bell-shaped curve that we can fit, with some mean and some variance parameter sigma. So what I mean by taking the log transform is really that if I have some feature x1 and then the histogram of x1 looks like this, then I might take my feature x1 and replace it with log of x1, and this is my new x1 that I'll plot the histogram of on the right. This looks much more Gaussian. And rather than just the log transform, some other things you could do might be, let's say I have a different feature x2, maybe I replace that with log x plus 1, or more generally with log x, that's x2, plus some constant c, and this constant could be something that I play with to try to make it look as Gaussian as possible. Or for a different feature x3, maybe I replace it with x3, I might take the square root. Square root is just x3 to the power of 1/2, right? And this 1/2 is another example of a parameter I can play with. So I have, x4, maybe I'll instead replace that with x4 to the power of something else, maybe to the power of 1/3. And all of these, this exponent parameter or the c parameter, all of these are examples of parameters you can play with in order to make your data look a little bit more Gaussian. So let me show you a live demo of how I'd actually go about playing around with my data to make it look more Gaussian. So I have already loaded into Octave here a set of features x. So I have 1,000 examples loaded over there. So let's plot a histogram of my data. I'm going to use the histx command. So there's my histogram. By default, I think this uses 10 bins in histogram, but I want to see a more fine-grained histogram. So I'm going to use hist of x comma 50. So this plots it in 50 different bins. Okay, that looks better. Now this doesn't look very Gaussian, does it? So let's start playing around with the data. Let's try hist of x to the 0.5. So I'm going to take the square root of the data and plot that histogram. And okay, it looks a little bit more Gaussian, but not quite there. So let's play with the 0.5 parameter. I'm going to set this to 0.2. Looks a little bit more Gaussian. Let's reduce a little bit more. 0.1. Yeah, that looks pretty good. I could actually just use 0.1. Well, let's reduce it to 0.05. And okay, this looks pretty Gaussian. So I could define a new feature, which is x new equals x element-wise exponentiation to the 0.05, and now my new feature x new looks more Gaussian than my previous one, and I might instead use this new feature to feed into my anomaly detection algorithm. And of course, there's more than one way to do this. You could also have hist of log of x. That's another example of a transformation you could use, and that also looks pretty Gaussian, so I could also define x new equals log of x, and that would be another pretty good choice of feature to use. So to summarize, if you plot a histogram with the data and find that it looks pretty non-Gaussian, it's worth playing around a little bit with different transformations like these to see if you can make your data look a little bit more Gaussian before you feed it to your learning algorithm. Although even if you don't, it might work okay, but I usually do take this step. Now the second thing I want to talk about is how do you come up with features for an anomaly detection algorithm. And the way I often do so is via an error analysis procedure. So what I mean by that is this is really similar to the error analysis procedure that we had for supervised learning, where we would train a complete algorithm and run the algorithm on a cross-validation set and look at the examples it gets wrong and see if we can come up with extra features to help the algorithm do better on the examples that it got wrong in the cross-validation set. So let's look through let's try to reason through an example of this process. In anomaly detection, we're hoping that P of x will be large for the normal examples and it'll be small for the anomalous examples. And so a pretty common problem would be if P of x is comparable, maybe both are large for both the normal and the anomalous examples. Let's look at a specific example of that. Let's say that this is my unlabeled data. So here I have just one feature x1. And so I'm going to fit a Gaussian to this. And maybe my Gaussian that fit to my data looks like that. And now, let's say I have an anomalous example. Let's say my anomalous example takes on an x value of 2.5. So I'm going to plot my anomalous example there. And it's kind of buried in the middle of a bunch of normal examples. And so this anomalous example that I've drawn in green, it gets a pretty high probability, right? It's the height of the blue curve. And the algorithm fails to flag this as an anomalous example. Now, if this were maybe aircraft engine manufacturing or something, what I would do is I would actually look at my training examples and look at what went wrong with that particular aircraft engine and see if looking at that example can inspire me to come up with a new feature X2 that helps to distinguish between this bad example compared to the rest of my red examples, compared to all of my normal aircraft engines. And if I manage to do so, the hope would be then that if I can create a new feature X2, so that when I replot my data, if I take all my normal examples, like my training set, hopefully I find that all my training examples are these red crosses here, and hopefully if I find that for my anomalous example, the feature X2 takes on a very unusual value. So for my green example here, this anomaly, right, my X1 value is still 2.5, but maybe my X2 value, hopefully it takes on a very large value, like 3.5 over there, or a very small value. But now, if I model my data, I'll find that my anomaly detection algorithm gives high probability, to data in the central region, slightly low probability to that, slightly low probability to that, an example, and then an example that's all the way out there, my algorithm will now give very low probability to. And so the process of this is really, look at the mistakes that it's making, look at the anomaly that the algorithm is failing to flag, and see if that inspires you to create some new feature. So find something unusual about that aircraft engine and use that to create a new feature, so that with this new feature it becomes easier to distinguish the anomalies from your good examples. And so that's the process of error analysis and using that to create new features for anomaly detection. Finally, let me share with you my thinking on how I usually go about choosing features for anomaly detection. So usually the way I think about choosing features is I want to choose features that might take on either very, very large values or very, very small values for examples that I think might turn out to be anomalies. So let's use our example again of monitoring the computers in a data center. And so with lots of machines, maybe thousands or tens of thousands of machines in a data center. And we want to know if one of the machines, one of our computers is acting up, so doing something strange. So here are examples of features we might choose, right? Maybe a memory use, number of disk accesses, CPU load, network traffic. But now let's say that I suspect one of the failure cases, let's say that in my data set, I think that CPU load and network traffic tend to grow linearly with each other. Maybe I'm running a bunch of web servers, and so if one of my servers is serving a lot of users, they'll have a very high CPU load and they'll have a very high network traffic. But let's say I have a suspicion that one of the failure cases is if one of my computers has a job that gets stuck in some infinite loops. If I think one of the failure cases is one of the machines, one of my web server code gets stuck in some infinite loop, and so the CPU load grows, but the network traffic doesn't, because it's just spinning its wheels and doing a lot of CPU work, stuck in some infinite loop. In that case, to detect that type of anomaly, I might create a new feature, X5, which might be CPU load divided by network traffic. And so here, X5 will take on an unusually large value if one of the machines has a very large CPU load but not that much network traffic. And so this will be a feature that will help your anomaly detection capture a certain type of anomaly. And you can also get creative and come up with other features as well. Like maybe I have a feature X6 that's CPU load squared divided by network traffic. And this would be another variant of a feature like X5 to try to capture anomalies where one of your machines has a very high CPU load but maybe doesn't have a commensurately large network traffic. And by creating features like these, you can start to capture anomalies that correspond to particular unusual combinations of values of the features. So in this video, we talked about how to take a feature and maybe transform it a little bit so that it becomes a bit more Gaussian before feeding into an anomaly detection algorithm, and also the error analysis in this process of creating features to try to capture different types of anomalies. And with these sorts of guidelines,
Raja berapa tuh?
Hopefully that will help you to choose good. In this and the next video, I'd like to tell you about one possible extension to the anomaly detection algorithm that we've developed so far. This extension uses something called the multivariate Gaussian distribution. It has some advantages and some disadvantages, and it can sometimes catch some anomalies that the earlier algorithm didn't. To motivate this, let's start with an example. Let's say that our unlabeled data looks like what I plotted here, and I'm going to use the example of monitoring machines in the data center, monitoring computers in the data center. So my two features are x1, which is the CPU load, and x2, which is maybe the memory use. So if I take my two features, x1 and x2, and if I model them as Gaussians, then here's a plot of my x1 features, here's a plot of my x2 features, and so if I fit a Gaussian to that, maybe I'll get a Gaussian like this. So here's p of x1, which depends on my parameters mu1 and sigma squared is 1. And here's my memory use. Maybe I get a Gaussian that looks like this. And this is my p of x2, which depends on mu2 and sigma squared 2. And so this is how the anomaly detection algorithm models x1 and x2. Now let's say that in the test set I have an example that looks like this. Right, the location of that green cross. So the value of x1 is about 0.4 and the value of x2 is about 1.5. Now if you look at the data, it looks like most of the data lies in this region, and so that green cross is pretty far away from any of the data I've seen. It looks like that should be raising an anomaly, right? So in my data, in the data of my good examples, it looks like the CPU load and the memory use, they sort of grow linearly with each other. So if I have a machine using lots of CPU, memory use will also be very high. Whereas this example, this green example, it looks like here the CPU load is very low, but the memory use is very high, and I just have not seen that before in my training set. It looks like that should be an anomaly. But let's see what the anomaly detection algorithm will do. Well, for the CPU load, it puts it at around there, 0.5. And this reasonably high probability is not that far from other examples we've seen maybe. Whereas for the memory use, I guess probably 0.5. Whereas for the memory use, it's about 1.5, which is there. Again, is out towards the tail of the Gaussian, but the value here is not that different from many other examples we've seen. And so P of x1 will be pretty high, reasonably high. P of x2 will be reasonably high. I mean, if you look at this plot, right, this point here, it doesn't look that bad. And if you look at this plot, across here, it doesn't look that bad. I mean, I have had examples with even greater memory use or with even less CPU use, and so this example doesn't look that anomalous. And so anomaly detection algorithm will fail to flag this point as an anomaly. And it turns out that what our anomaly detection algorithm is doing is it's not realizing that this blue ellipse shows the high probability region. Instead, what it thinks is that examples here are high probability, and examples the next circle out are somewhat lower probability, and examples here are even lower probability. And somehow, things that are green cross there is pretty high probability. And in particular, it tends to think that, everything in this region, everything on the line that I'm circling over has about equal probability, and it doesn't realize that something out here actually has much lower probability than something over there. So in order to fix this, we're going to develop a modified version of the anomaly detection algorithm using something called the multivariate Gaussian distribution, also called the multivariate normal distribution. So here's what we're going to do. We have features x which are in Rn, and instead of modeling p of x1, p of x2 separately, we're going to model p of x all in one go, so model p of x all at the same time. So the parameters of the multivariate Gaussian distribution are mu, which is a vector, and sigma, which is an n by n matrix called a covariance matrix. And this is similar to the covariance matrix that we saw when we were working with the PCA, with the principal components analysis algorithm. For the sake of completeness, let me just write out the formula for the multivariate Gaussian distribution. So we say that probability of x, and this is parameterized by my parameters mu and sigma, that the probability of x is equal to, once again, there's absolutely no need to memorize this formula. You can look it up whenever you need to use it, but this is what the probability of x looks like. Transpose inverse x minus mu. And this thing here, the absolute value of sigma, this thing here, when I write this symbol, this is called the determinant of sigma. And this is a mathematical function of a matrix, and you really don't need to know what the determinant of a matrix is, but really all you need to know is that you can compute it in octave by using the octave command det of sigma. Okay, and again, just be clear, right? In this expression, these sigmas here, these are this n by n matrix. This is not a summation. The sigma there is an n by n matrix. So that's the formula for p of x. But more interestingly, or more importantly, is what does p of x actually look like? Let's look at some examples of multivariate or Gaussian distributions. So let's take a two-dimensional example. So if I have n equals 2, I have two features, x1 and x2. Let's say I set mu to be equal to 0 and sigma to be equal to this matrix here, with 1s on the diagonals and 0s on the off diagonals. This matrix is sometimes also called the identity matrix. In that case, p of x will look like this. And what I'm showing in this figure is, for a specific value of x1 and for a specific value of x2, the height of this surface gives the value of p of x. And so with this setting of the parameters, p of x is highest when x1 and x2 equals 0. So that's the peak of this Gaussian distribution. And the probability falls off with this sort of two-dimensional Gaussian, or this bell-shaped, two-dimensional bell-shaped surface. Down below is the same thing but plotted using a contour plot instead, or plotted using the different colors. And so this heavy, intense red in the middle corresponds to the highest values, and then the values decrease, with the yellow being slightly lower values, the cyan being lower values, and this deep blue being the lowest value. So this is really the same figure but plotted, viewed from the top instead, using colors instead. And so with this distribution, you see that it places most of the probability near 0, 0, and then as you go away from 0, 0, the probability of x1 and x2 goes down. Now let's try varying some of the parameters and see what happens. So let's take sigma and change it. So let's say sigma shrinks a little bit. Sigma is a covariance matrix, and so it measures the variance of the variability of the features x1 and x2. So if you shrink sigma, then what you get is that the width of this bump diminishes, and the height also increases a bit because the area under the surface is equal to 1. So the integral of the volume under the surface is equal to 1 because probability distribution must integrate to 1. But so if you shrink the variance, it's kind of like shrinking sigma squared. You end up with a narrower distribution, one that's a little bit taller. And so you see here also the concentric ellipses has shrunk a little bit. Whereas in contrast, if you were to increase sigma to 2 on the diagonal, so this is now 2 times the identity, then you end up with a much wider, much flatter Gaussian, and so the width of this is much wider. This is hard to see, but this is still a bell-shaped bump that's just flattened out a lot, and it's become much wider. And so the variance here, the variability of x1 and x2 just becomes wider. Here are a few more examples. Now let's try varying one of the elements of sigma at a time. Let's say I set sigma to 0.6 there and 1 over there. What this does is this reduces the variance of the first feature x1 while keeping the variance of the second feature x2 the same. And so with this setting of parameters, you can model things like that. x1 has smaller variance and x2 has larger variance. Whereas if I do this, if I set this matrix to 2, 1, then you can also model examples where, here it looks like x1 can take on a large range of values, whereas x2 takes on a relatively narrow range of values, and that's reflected in this figure as well, where the distribution falls off more slowly as x1 moves away from 0, and it falls off very rapidly as x2 moves away from 0. And similarly, if we were to modify this element of the matrix instead, then it's similar to the previous slide, except that here we're playing around. Here we're saying that x2 can take on a very small range of values, and so here this is 0.6, where notice now x2 tends to take on a much smaller range of values than the original example. Whereas if we were to set sigma to equal to 2, then that's like saying that x2 has a much larger range of values. Now, one of the cool things about the multivariate Gaussian distribution is that you can also use it to model correlations between the data. That is, you can use it to model the fact that x1 and x2 tend to be highly correlated with each other, for example. So specifically, if you start to change the off-diagonal entries of this covariance matrix, you can get a different type of Gaussian distribution. And so as I increase the off-diagonal entries from 0.5 to 0.8, what I get is a distribution that's more and more thinly peaked along this sort of x equals y line. Right? And so here the contour says that x and y tend to grow together, and the things with large probability are if either x1 is large and y2 is large, or x1 is small and y2 is small, or somewhere in between. And as this entry 0.8 gets large, you get a Gaussian distribution that's sort of where all the probability lies on this sort of narrow region where x is approximately equal to off-diagonal entries from 0.5 to 0.8 of this covariance matrix, and you can get a different type of Gaussian distribution. And so as I increase the off-diagonal entries from 0.5 to 0.8, what I get is were to modify that. You can also use it, whereas if we were to set sigma to equal to 2, then that's like saying that x2 has a much larger range of values. Now, one of the cool things about the multivariate Gaussian distribution is that you can also use it to model correlations between the data. That is, you can use it to model the fact that x1 and x2 tend to be highly correlated with each other, for example. So specifically, if you start to change the off-diagonal entries of this covariance matrix, you can get a different type of Gaussian distribution. And so as I increase the off-diagonal entries from 0.5 to 0.8, what I get is a distribution that's more and more thinly peaked along this sort of x equals y line. And so here the contour says that x and y tend to grow together, and the things with large probability are if either x1 is large and y2 is large, or x1 is small and y2 is small, or somewhere in between. And as this entry 0.8 gets large, you get a Gaussian distribution that's so where all the probability lies on this sort of narrow region where x is approximately equal to y. Kind of does a very tall, thin distribution, lying mostly along this central region where x is close to y. So this is if we set these entries to be positive entries. In contrast, if we set these to negative values, as I decreases the minus 0.5 down to minus 0.8, then what we get is a model where we put most of the probability in this sort of negative x1 and x2 correlation region. And so most of the probability now lies in this region where x1 is about equal to minus x2 rather than x1 equals x2. And so this captures a sort of negative correlation between x1 and x2. And so this is hopefully this gives you a sense of the different distribution. These to negative valuation, that's so where all the probability lies on this sort of narrow region where between x1 and x2. These to negative mostly along this central multivariate Gaussian distribution can capture. So far we've been varying the covariance matrix sigma. As if we vary the values of mu, then that varies the peak of the distribution. So if mu equals 0, 0.5, the peak is at x1 equals 0 and x2 equals 0.5, and so the peak or the center of this distribution has shifted. And if mu was 1.5 minus 0.5, then again similarly the peak of the distribution has now shifted to a different location corresponding to where x1 is 1.5 and x2 is minus 0.5. So varying the mu parameter just shifts around the center of this whole distribution. So hopefully looking at all these different pictures gives you a sense of the sort of probability distributions that the multivariate Gaussian distribution allows you to capture. In the last video, we talked about the multivariate Gaussian distribution and saw some examples of the sorts of distributions you can model as you vary the parameters mu and sigma. In this video, let's take those ideas and apply them to develop a different anomaly detection algorithm. To recap, the multivariate Gaussian distribution, or the multivariate normal distribution, has two parameters mu and sigma, where mu is an n-dimensional vector, and sigma, the covariance matrix, is an n by n matrix. And here's the formula for the probability of x as parameterized by mu and sigma. And as you vary mu and sigma, you can get a range of different distributions. Like, these are three examples of the ones that we saw in the previous video. So let's talk about the parameter fitting, or the parameter estimation problem. The question, as usual, is if I have a set of examples x1 through xm, and here each of these examples is an n-dimensional vector, and I think my examples come from a multivariate Gaussian distribution. How do I try to estimate my parameters mu and sigma? Well, the standard formulas for estimating them is you set mu to be just the average of your training examples, and you set sigma to be equal to this. And this is actually just like the sigma that we had written out when we were using the PCA, or the principal components analysis algorithm. So you just plug in these two formulas, and this would give you your estimated parameter mu and your estimated parameter sigma. So given the data set, here's how you estimate mu and sigma. Let's take this method and just plug it into an anomaly detection algorithm. So how do we put all this together to develop an anomaly detection algorithm? Here's what we do. First, we take our training set and we fit the model, we fit P of x by setting mu and sigma as described on the previous slide. Next, when you're given a new example x, so if you're given a test example, let's take an earlier example. Let's say I have a new example out here, and that's my test example. Given the new example x, what we're going to do is compute P of x using this formula for the multivariate Gaussian distribution. And then if P of x is very small, then we flag it as an anomaly, whereas if P of x is greater than that parameter epsilon, then we don't flag it as an anomaly. So it turns out if we were to fit a multivariate Gaussian distribution to this data set, to just the red crosses, right, not the green example, you end up with a Gaussian distribution that places loss of probability in the central region, slightly less probability here, slightly less probability here, slightly less probability here, and very low probability at the point that's way out here. And so if you apply the multivariate Gaussian distribution to this example, it will actually correctly flag that example as an anomaly. Finally, it's worth saying a few words about what is the relationship between the multivariate Gaussian distribution model and the central region. slightly less probability here, slightly less probability here, slightly less probability here, and very low probability at the point that's way out here. And so if you apply the multivariate Gaussian distribution to this example, it will actually correctly flag that example as an anomaly. Finally, it's worth saying a few words about what is the relationship between the multivariate Gaussian distribution model and the original model, where we were modeling P of x as a product of this P of x1, P of x2, up to P of xn. It turns out that you can prove mathematically, I'm not going to do the proof here, but you can prove mathematically that there's a relationship between the multivariate Gaussian model and this original one. And in particular, it turns out that the original model corresponds to multivariate Gaussians where the contours of the Gaussian are always axis aligned. Right? So all three of these are examples of Gaussian distributions that you can fit using the original model. It turns out that that corresponds to multivariate Gaussian where the ellipses here, the contours of this distribution. It turns out that this model actually corresponds to a special case of a multivariate Gaussian distribution. And in particular, the special case is defined by constraining the distribution of P of x, the multivariate Gaussian distribution of P of x, so that the contours of the probability density function, of the probability distribution function, are axis aligned. And so you can get a P of x with a multivariate Gaussian that looks like this, or like this, or like this. And you notice that in all three of these examples, these ellipses, or these ovals that I'm drawing, have their axes aligned with the x1, x2 axes. And what we do not have is a set of contours that are at an angle, right? And this corresponded to examples where sigma is equal to 1, 1, 0.8, 0.8, let's say, with non-zero elements on the off diagonals. So it turns out that it's possible to show mathematically that this model actually is the same as a multivariate Gaussian distribution, but with a constraint. And the constraint is that the covariance matrix sigma must have zeros on the off-diagonal elements. In particular, the covariance matrix sigma, this thing here, it would be sigma squared 1, sigma squared 2, down to sigma squared n. And then everything on the off-diagonal entries, all of these elements above and below the diagonal of that matrix, all of those are going to be 0. And in fact, if you take these values of sigma, sigma squared 1, sigma squared 2, down to sigma squared n, and plug them into here, and plug them into this covariance matrix, then the two models are actually identical. That is, this new model, using the multivariate Gaussian distribution, corresponds exactly to the old model if the covariance matrix sigma has only 0 elements. Off the diagonals, and in pictures that corresponds to having Gaussian distributions where the contours of this distribution function are axis aligned, so you aren't allowed to model the correlations between the different features. So in that sense, the original model is actually a special case of this multivariate Gaussian model. So when would you use each of these two models? So when would you use the original model, and when would you use the multivariate Gaussian model? The original model is probably used somewhat more often, and whereas the multivariate Gaussian distribution is used somewhat less, but it has the advantage of being able to capture correlations between features. So suppose you want to capture anomalies where you have different features, say where features x1, x2 take on unusual combinations of values. So in the earlier example, we had that example where the anomaly was with the CPU load and the memory use taking on unusual combinations of values. If you want to use the original model to capture that, then what you need to do is create an extra feature, such as x3 equals x1 over x2, equals maybe the CPU load, divided by the memory used or something. And you need to create extra features if there's unusual combinations of values, where x1 and x2 take on an unusual combination of values, even though x1 by itself and x2 by itself looks like it's taking a perfectly normal value. But if you're willing to spend the time to manually create an extra feature like this, then the original model will work fine. Whereas in contrast, the multivariate Gaussian model can automatically capture correlations between different features. But the original model has some other, maybe more significant advantages too. And one huge advantage of the original model is that it is computationally cheaper. And another view on this is that it scales better to very large values of n, to very large numbers of features. And so even if n were, say, 10,000, or even if n were equal to 100,000, the original model will usually work just fine. Whereas in contrast, for the multivariate Gaussian model, notice here, for example, that we need to compute the inverse of the matrix sigma, where sigma is an n by n matrix. And so computing sigma, if sigma is a 100,000 by 100,000 matrix, that's going to be very computationally expensive. And so the multivariate Gaussian model scales less well to large values of n. And finally, for the original model, it turns out to work okay even if you have a relatively small training set. This is a small unlabeled example that we use to model P of x, of course. This just works fine even if m is maybe 50, 100, it works fine. Whereas for the multivariate Gaussian, it is sort of a mathematical property of the algorithm that you must have m greater than n, so that the number of examples is greater than the number of features you have. And there's a mathematical property of the way we estimate the parameters that if this is not true, so if m is less than or equal to n, then this matrix isn't even invertible. That is, this matrix is singular, and so you can't even use the multivariate Gaussian model unless you make some changes to it. But a typical rule of thumb that I use is, I would use the multivariate Gaussian model only if m is much greater than n. So this is sort of the narrow mathematical requirement, but in practice I would use the multivariate Gaussian model only if m were quite a bit bigger than n. So if m were greater than or equal to 10 times n, let's say, might be a reasonable rule of thumb. And if it doesn't satisfy this, then the multivariate Gaussian model has a lot of parameters, right? So this covariance matrix sigma is an n by n matrix, so it has roughly n squared parameters. Because it's a symmetric matrix, it's actually closer to n squared over 2 parameters, but this is a lot of parameters, and so you need to make sure that you have a fairly large value for m. Make sure you have enough data to fit all these parameters. And m greater than or equal to 10n would be a reasonable rule of thumb to make sure that you can estimate this covariance matrix sigma reasonably well. So in practice, the original model shown on the left that is used more often, and if you suspect that you need to capture correlations between features, what people will often do is just manually design extra features like these to capture specific unusual combinations of values. But in problems where you have a very large training set where m is very large and n is not too large, then the multivariate Gaussian model is well worth considering and may work better as well, and can save you from having to spend the time to manually create extra features in case the anomalies turn out to be captured by unusual combinations of values of the features. Finally, I just want to briefly mention one somewhat technical property, but if you fit a multivariate Gaussian model and if you find that the covariance matrix sigma is singular, or you find it is non-invertible, there are usually 2 cases for this. One is if it's failing to satisfy this m greater than n condition, and the second case is if you have redundant features. So by redundant features, I mean if you have 2 features that are same, somehow you accidentally made 2 copies of the feature, so the x1 is just equal to x2. Or if you have redundant features, and maybe maybe feature x3 is equal to feature x4 plus feature x5. Okay, so if you have highly redundant features like these, where if x3 is equal to x4 plus x5, well, x3 doesn't contain any extra information, right? You take these 2 other features and you add them together. And if you have this sort of redundant features, duplicated features, or this sort of features, then sigma may be non-invertible. And so there's a debugging step. This should very rarely happen, so you probably won't run into this. It's very unlikely you have to worry about this. But in case you implement a multivariate Gaussian model and you find that sigma is non-invertible, what I would do is first make sure that n is quite a bit bigger than n. And if it is, then the second thing I do is just check for redundant features. And so if I have two features that are equal, just get rid of one of them. Or if you have redundant features like these, x2 equals x plus x5, just get rid of the redundant feature, and then it should work fine again. As an aside, for those of you that are experts in linear algebra, by redundant features, what I mean is the formal term is features that are linearly dependent. But in practice, what that really means is one of these problems, tripping up the algorithm, and if you just make your features non-redundant, that should solve the problem of sigma being non-invertible. But once again, the odds of you running into this at all are pretty low, so chances are you can just apply the multivariate Gaussian model without having to worry about sigma being non-invertible, so long as m is greater than or equal to n. So that's it. For anomaly detection with the multivariate Gaussian distribution, and if you apply this method, you'll be able to have an anomaly detection algorithm that automatically captures positive and negative correlations between your different features and In this next set of videos, I'd like to tell you about recommender systems. There were two reasons, I had two motivations for why I wanted to talk about recommender systems. The first is just that it's an important application of machine learning. Over the last few years, occasionally I visit different technology companies here in Silicon Valley, and I often talk to people working on machine learning applications there. And so I've asked people, what are your most important applications of machine learning, or what are the machine learning applications that you would most like to get an improvement in the performance of? And one of the most frequent answers I heard was that there are many groups out in Silicon Valley now trying to build better recommender systems. So if you think about what the websites I heard was that there are many groups out in Silicon Valley now trying to build better recommender systems. So if you think about what the websites of like Amazon or what Netflix or what eBay or what iTunes Genius made by Apple does, there are many websites or systems that try to recommend new products to you. So Amazon recommends new books to you, Netflix tries to recommend new movies to you, and so on. And these sorts of recommender systems that look at what books you may have purchased in the past or what movies you've rated in the past, but these sorts of systems that are responsible for today a substantial fraction of Amazon's revenue. And for a company like Netflix, the recommendations that they make to the users is also responsible for a substantial fraction of the movies watched by the users. And so an improvement in the performance of a recommender system can have a substantial and immediate impact on the bottom line of many of these companies. Recommender systems is kind of a funny problem. Within academic machine learning, so that if you go to an academic machine learning conference, the problem of recommender systems actually receives relatively little attention, or at least it's sort of a smallish fraction of what goes on within academia. But if you look at what's happening in many technology companies, the ability to build these systems seems to be a high priority for many companies. And that's one of the reasons why I want to talk about it in this class. The second reason that I want to talk about recommender systems is that as we approach the last few sets of videos of this class, I wanted to talk about a few of the big ideas in machine learning and share with you, some of the big ideas in machine learning. And we've already seen in this class that features are important for machine learning, and the features you choose will have a big effect on the performance of your learning algorithm. So there's this big idea in machine learning, which is that for some problems, maybe not all problems, for some problems, there are algorithms that can try to automatically learn a good set of features for you. So rather than trying to hand design or hand code the features, which is mostly what we've been doing so far, there are a few settings where you might be able to have an algorithm just learn what features to use. And recommender systems is just one example of that sort of setting. There are many others, but in going through recommender systems, we'll be able to go a little bit into this idea of learning the features, and you'll be able to see at least one example of this, I think, big idea in machine learning as well. So, without further ado, let's get started and talk about the recommender system problem formulation. As my running example, I'm going to use the problem of predicting movie ratings. So here's a problem. Imagine that you're a website or a company that sells or rents out movies and what have you. And so, Amazon and Netflix and I think iTunes are all examples of companies that do this. And let's say you let your users rate different movies using a 1 to 5 star rating. So using something 1, 2, 3, 4, or 5 stars. In order to make this example just a little bit nicer, I'm going to allow 0 to 5 stars as well, because that just makes some of the math come out nicer. Although most of these websites use a 1 to 5 star scale. So here I have 5 movies. Love at Last, Romance Forever, Cute Puppies of Love, Non-Stop Car Chases, and Souls vs. Karate. And we have 4 users, which calling Alice, Bob, Carol, and Dave with initials A, B, C, and D. We'll call them users 1, 2, 3, and 4. So let's say Alice really likes Love It Lost and rates that 5 stars, really likes Romance Forever, rates that 5 stars. She did not watch Cute Puppies of Love, but did not rate it, so we don't have a rating for that. And Alice really did not like Non-Stop Car Chases or Swords vs. Karate. And different user, Bob, user 2, maybe rates a different set of movies. Maybe he likes Love It Lost, did not watch Romance Forever, gives that a rating of 4, a 0, a 0. And maybe our third user rates these 0, did not watch that one, 0, 5, 5. And let's just fill in some of the numbers. Okay. And so just to introduce a bit of notation, this notation we'll be using throughout, I'm going to use NU to denote the number of users. So in this example, NU will be equal to 4. So the U subscript stands for users. And an M I'm going to use to denote the number of movies. So here I have 5 movies, so NM equals 5. And for this example, I have loosely 3 maybe romantic comedy movies and 2 action movies. And if you look at this small example, it looks like Alice and Bob are giving high ratings to these romantic comedies or movies about love, and giving very low ratings about the action movies. And for Carol and Dave is the opposite, right? Carol and Dave, users 3 and 4, really like the action movies and give them high ratings, but don't like the romance and love type movies as much. Specifically, in the recommender system problem, we are given the following data. Our data comprises the following. We have these values Rij, and Rij is 1 if user J has rated movie I. So our users rate only some of the movies, and so we don't have ratings for those movies. And whenever Rij is equal to 1, whenever user J has rated movie I, we also get this number Yij, which is the rating given by user J to movie I. And so Yij will be a number from 0 up to 5, depending on the star rating, 0 to 5 stars that the user gave that particular movie. So the recommender system problem is, given this data set, that is given these Rijs and the Yijs, to look through your data and look at all the movie ratings that are missing, and to try to predict what these values of the question mark should be. In this particular example, I have a very small number of movies and a very small number of users, and so most users have rated most movies, but in a realistic setting, each of your users may have rated only a minuscule fraction of the movies. But looking at this data, if Alice and Bob both like the romantic movies, maybe we think that Alice would have given this a 5, maybe we think Bob would have given this a 4.5 or some high value, whereas we think maybe Carol and Dave would have given these very low ratings, and Dave, well, if Dave really likes action movies, maybe he would have given Swords and Karate a 4 rating or maybe a 5 rating. Okay, and so our job in developing a recommender system is to come up with a learning algorithm that can automatically fill in these missing values for us, so that we can look at, say, the movies that the user has not yet watched and recommend new movies to that user to watch, and try to predict what else might be interesting to a user. So that's the formalism of the recommender system problem. In the next video, we'll start to develop a learning algorithm to address this problem. In the last video, we talked about the recommender system problem, where, for example, you may have a set of movies and you may have a set of users, each of whom has rated some subset of the movies. They've rated the movies 1 to 5 stars or 0 to 5 stars. And what we would like to do is look at these users and predict how they would have rated other movies that they have not yet rated. In this video, I'd like to talk about our first approach to building a recommender system. This approach is called content-based recommendations. Here's our data set from before, and just to remind you of a bit of notation, I was using NU to denote the number of users, and so that's equal to 4, and NM to denote the number of movies. I have 5 movies. So how do I predict what these missing values would be? Let's suppose that for each of these movies, I have a set of features for them. In particular, let's say that for each of the movies I have 2 features which I'm going to denote x1 and x2, where x1 measures the degree to which a movie is a romantic movie and x2 measures the degree to which a movie is an action movie. So if you take a movie Love That Lasts, it's 0.9 rating on the romance scale, so it's a highly romantic movie, but 0 on the action scale, so almost no action in that movie. Romance Forever, so 1.0, a lot of romance, and 0.01 action. I don't know, maybe there's a minor car crash in that movie or something, so it's a little bit of action. Skipping one, let's do Swords versus Karate. Maybe that has a 0 romance rating, no romance at all in that, but plenty of action. And non-stop car chases. Maybe again there's a tiny bit of romance in that movie, but mainly action. And Cute Puppies of Love. Again, mainly a romance movie with no action at all. So if we have features like these, then each movie can be represented with a feature vector. Let's take movie 1. So let's call these movies, movies 1, 2, 3, 4, and 5. But my first movie, Love At Last, I have my 2 features, 0.9 and 0. And so these are features x1 and x2, and let's add an extra feature as usual, which is my intercept term feature x0, which is equal to 1. And so putting these together, I would then have a feature x1. The superscript 1 denotes is the feature vector for my first movie, and this feature vector is equal to 1. The first 1 there is this intercept term, and then my 2 features 0.9, 0, like so. So for Love At Last, I would have a feature vector x1. For the movie Romance Forever, I may have a separate feature vector x2, and so on. And for Swords versus Karate, I would have a different feature vector x superscript 5. Also, consistent with our earlier notation that we were using, we're going to set n to be the number of features not counting this x0 intercept term, and so n is equal to 2 because we have 2 features, x1 and x2, capturing the degree of romance and the degree of action in each movie. Now, in order to make predictions, here's one thing we could do, which is that we could treat predicting the ratings of each user as a separate linear regression problem. So specifically, let's say that for each user j, we're going to learn a parameter vector theta j, which would be in R3 in this case. More generally, theta j would be in Rn plus 1, where n is the number of features, not counting the intercept term. And we're going to predict user j as rating the movie I with just the inner product between the parameters vector theta and the features xi. So let's take a specific example. Let's take user 1. So that would be Alice, and associated with Alice would be some parameter vector theta 1. And our second user, Bob, will be associated with a different parameter vector theta 2. Carol will be associated with a different parameter vector theta 3, and Dave a different parameter vector theta 4. So let's say we want to make a prediction for what Alice will think of the movie Cute Puppies of Love. Well, that movie is going to have some parameter vector x3, where we have that x3 is going to be equal to 1, which is for intercept term, and then 0.99, and then 0. And let's say for this example, let's say that we've somehow already gotten a parameter vector theta 1 for Alice. We'll say later exactly how we come up with this parameter vector. But let's just say for now that some unspecified learning algorithm has learned the parameter vector theta 1 and is equal to this 0, 5, 0. So our prediction for this entry is going to be equal to theta 1, that is Alice's parameter vector, transpose x3, that is the feature vector for the Q puppies of love movie number 3. And so the inner product between these two vectors is going to be 5 times 0.99, which is equal to 4.95. And so my prediction for this value over here is going to be 4.95. Maybe that seems like a reasonable value if indeed this is my parameter vector theta 1. So all we're doing here is we're applying a different copy of essentially linear regression for each user, and we're saying that what Alice does is Alice has some parameter vector theta 1 that she uses, that we use to predict her ratings as a function of how romantic and how action-packed the movie is. And Bob and Carol and Dave, each of them have a different linear function of the romanticness and actionness, or degree of romance and the degree of action in a movie, and that's how we're going to predict their star ratings. More formally, romanticness and actionness is so all this is this value over here. A different parameter vector theta 3 and Dave a different parameter vector theta 4. So let's say we want to make a prediction for what Alice will think of the movie Q Puppies of Love. Well, that movie is going to have some parameter vector x3, where we have that x3 is going to be equal to 1, which is my intercept term, and then 0.99 and then 0. And let's say for this example, let's say that we've somehow already gotten a parameter vector theta 1 for Alice. We'll say later exactly how we come up with this parameter vector. But let's just say for now that some unspecified learning algorithm has learned the parameter vector theta 1 and is equal to this 0, 5, 0. So our prediction for this entry is going to be equal to theta 1, that is Alice's parameter vector, transpose x3, that is the feature vector for the Q Puppies of Love movie number 3. And so the inner vector, and we're saying that what Alice, which is equal to 4.95. And so my prediction for this value over here is going to be 4.95. Maybe that would be there for the Q Puppies of Love movie. How we're going to predict their star ratings. of the romantic prediction term, and then 0.99 and then 0. And let's say for this example, let's say that we've somehow already gotten a parameter vector theta 1 for Alice. We'll say later exactly how we come up with this parameter vector. But let's just say for now that some unspecified learning algorithm has learned the parameter vector theta 1 and is equal to the 0, 5, 0. So our prediction, more formally, copy of essentially linear prediction for this value over here is going to be 4.95. Maybe that seems like a reasonable value if indeed this is my parameter vector theta 1. So all we're doing here is we're applying a different copy of essentially linear regression for each user, and we're saying that what Alice does is Alice has some parameter vector theta 1 that she uses, that we use to predict her ratings as a function of how romantic and how action-packed a movie is, and Bob and Carol and Dave, each of them have a different linear function of the romanticness as an actionness, or degree of romance, and the degree of action in a movie, and that's how we're going to predict their star ratings. More formally, romanticness and actionness, or degree of romance, and the degree of action in a movie, and that's how we're capturing the degree of romance. And so for love at last, I would piece of love. Romantic two features. Let's the feature early notation that we will use I would then have a feature x1. The superscript 1 denotes is the feature vector for my first movie, and this feature vector is equal to 1. The first one there is this intercept term, and then my two features 0.9, 0, like 0.5. But I have added x together. I would then have a feature x1. The superscript 1 denotes is the feature vector for my first movie, and this feature vector is equal to 1. The first one there is this intercept term, and then my two features 0.9. However, we have a separate feature vector x2, and so on, and for source with 5. Features not counting this x0 intercept term, and so n is equal to 2 because we have two features to do, which is that. Now, in order to make predictions, here's one thing we could do, which is that we could treat predicting the ratings of each user as a separate linear regression problem. So specifically, let's say that for each user j, we're going to learn a parameter vector theta j, which would be in R3 in this case. More generally, theta j would be in R and user 1. So that would be Alice, and a, which would be in R3 in this case. More generally, theta j would be in Rn plus 1, where n is the number of features, not counting the intercept term. And we're going to predict user j as rating movie I with just the inner product between the parameters vector theta and the features xi. So let's take a specific example. Let's take user 1. So that would be Alice, and associated with Alice would be some parameter vector theta 1, puppies of love. Well, that movie is going to have some parameter vector x3, where we have that x3 is going to be equal to 1, which of the movie Cute Puppies of Love. Well, that movie is, let's say we want to make a prediction for what Alice will think of the movie Cute Puppies of Love. Well, that movie is going to have some parameter vector x3, where we have that x3 is going to be equal to 1, which is my intercept term, and then 0.99 vector theta 1 for alpha. Say for this example, let's say that we've somehow already gotten a parameter vector theta 1 for Alice. We'll say later exactly how we come up with this parameter vector. But let's just say for now that some unspecified learning algorithm has learned the parameter vector theta 1 and is equal to the 0, 5, 0. So our prediction for this entry is going to be equal to theta 1, that is Alice's. This value over here is going to be 4 theta 1. The linear regression for each user, and we're saying that what Alice does is Alice has some parameter vector theta 1 that she uses, that we use to predict her ratings as a function of how romantic and how action-packed the movie is. And Bob and Carol and Dave, each of them have a different linear function of the romanticness and action. That's how we're going to predict their star ratings. More formally, here's how we can write down the problem. Our notation is that Rij is equal to 1 if user j has rated movie I, and Yij is the rating of that movie if that rating exists. That is, if that user has actually rated that movie. And on the previous slide, we also defined these theta j, which is a parameter for each user, xi, which is a feature vector for a specific movie, and for each user and each movie we predict that rating as follows. So let me just temporarily introduce one extra bit of notation, mj. We're going to use mj to denote the number of users rated by movie j. We don't need this notation only for this slide. Now, in order to learn the parameter vector for theta j, well, how can we do so? This is basically a linear regression problem. So what we can do is just choose a parameter vector theta j so that the predicted values here are as close as possible to the values that we observed in our training set, to the values we observed in our data. So let's write that down. In order to learn the parameter vector theta j, let's minimize over my parameter vector theta j of sum. And I want to sum over all movies that user j has rated. So we write this as sum over all values of I, that's a colon, Rij equals 1. So the way to read this summation index is, this is summation over all the values of I so that Rij is equal to 1. So this is really summing over all the movies that user j has rated. And then I'm going to compute theta j transpose xi. So that's the prediction of user j's rating on movie I, minus Yij, so that's the actual observed rating, squared. And then let me just divide by the number of movies that user j has actually rated. So this is divided by 1 over 2 mj. And so this is just like the least squares regressions. It's just like linear regression, where we want to choose the parameter vector theta j to minimize this type of squared error term. And if you want, we can also add in a regularization term, so it's a plus lambda over 2m. And this is really 2mj, because it's as if we have mj examples, right? Because if user j has rated that many movies, it's sort of like we have that many data points with which to fit the parameters theta j. And then let me add in my usual regularization term here of theta j k squared. As usual, this sum is from k equals 1 through n. So here, theta j is going to be an n plus 1 dimensional vector, where in our earlier example, n was equal to 2, but more generally, n is the number of features we have per movie. And so, as usual, we don't regularize over theta 0. We don't regularize over the bias terms. The sums from k equals 1 through n. So if you minimize this as a function of theta j, you get a good solution. You get a pretty good estimate of a parameter vector theta j with which to make predictions for user j's movie ratings. For recommender systems, I'm going to change this notation a little bit. So to simplify the subsequent math, I'm actually going to get rid of this term mj. So that's just a constant, right? So I can delete it without changing the value of theta j that I get out of this optimization. So you imagine taking this whole equation, taking this whole expression and multiplying it by mj and get rid of that constant. And when I minimize this, I should still get the same value of theta j as before. So just to repeat what we wrote on the previous slide, here's our optimization objective. In order to learn theta j, which is the parameter for user j, we're going to minimize over theta j of this optimization objective. So this is our usual squared error term, and then this is our regularization term. Now, of course, in building a recommender system, we don't just want to learn parameters for a single user. We want to learn parameters for all of my users. So I have n subscript u users. So I want to learn all of these parameters. And so what I'm going to do is take this optimization objective and just add an extra summation there. So this expression here with the 1/2 on top of this is exactly the same as what we had on top. Except that now, instead of just doing this for a specific user theta j, I'm going to sum my objective over all of my users and then minimize this overall optimization objective, minimize this overall cost function. And when I minimize this as a function of theta 1, theta 2, up to theta nu, I will get a separate parameter vector for each user. And I can then use that to make predictions for all of my users, for all of my n subscript u users. So putting everything together, this was our optimization objective on top. And to give this thing a name, I'm just going to call this j of theta 1 theta nu. So j, as usual, is my optimization objective, which I'm trying to minimize. Next, in order to actually do the minimization, if you were to derive the gradient descent updates, these are the equations that you would get. So you take theta j, k, and subtract from it alpha, which is the learning rate, times these terms over here on the right. So we have slightly different cases, so when k equals 0 and when k is not equal to 0, because our regularization term here regularizes only the values of theta jk for k not equal to 0. So we don't regularize theta 0. So we have slightly different updates for k equals 0 and k not equals 0. And this term over here, for example, is just the partial derivative with respect to your parameter, that of your optimization objective, right? And so this is just gradient descent, but and I've already computed the derivatives and plugged them into here. And if this and if these gradient descent updates look a lot like what we had for linear regression, that's because these are essentially the same as linear regression. The only minor difference is that for linear regression, we had these 1 over n terms. It's really would have been 1 over mj, but because earlier when we are deriving the optimization objective, we got rid of this. That's why we don't have this 1 over m term. But otherwise, it's really some of my training examples of the error times xk plus that regularization term, plus that term that the regularization term contributes to the derivative. And so if you're using gradient descent, here's how you can minimize the cost function j to learn all the parameters. And using these formulas for the derivatives, if you want, you can also plug them into a more advanced optimization algorithm like conjugate gradient or LBFGS or what have you, and use that to try to minimize the cost function j as well. So hopefully you now know how you can apply essentially a variation on linear regression in order to predict different movie ratings. In this video, we'll talk about an approach to building a recommender system that's called collaborative filtering. The algorithm that we're going to talk about has a very interesting property that it does what is called feature learning. And by that I mean that this will be an algorithm that can start to learn for itself what features to use. Here was the data set that we had, and we had assumed that for each movie, someone had come and told us how romantic that movie was and how much action there was in that movie. But as you can imagine, it can be very difficult and time-consuming and expensive to actually try to get someone to, watch each movie and tell you how romantic is each movie and how action-packed is each movie. And often you want even more features than just these two. So where do you get these features from? So let's change the problem a bit and suppose that we have a data set where we do not know the values of these features. So we're given a data set of movies and of how the users rated them, but we have no idea how romantic each movie is, and we have no idea how action-packed each movie is. So I've replaced all of these things with question marks. But now let's make a slightly different assumption. Let's say that we've gone to each of our users, and each of our users has told us how much they like romantic movies and how much they like action-packed movies. So Alice has associated a parameter vector theta1, Bob theta2, Carol theta3, Dave theta4. And let's say that we ask our users, let's say Alice tells us that she really likes romantic movies, and so there's a 5 there, which is the multiplier associated with x1. And let's say Alice tells us she really doesn't like action movies, so there's a 0 there. And Bob tells us something similar, so we have theta2 over here. Whereas Carol tells us that she really likes action movies, which is why there's a 5 there. That's the multiplier associated with x2. Remember, there's also x0 equals 1. And let's say that Carol tells us she doesn't like romantic movies, and so on. Similarly for Dave. So let's assume that somehow we can go to our users, and each user j just tells us what is the value of theta j for them. And so it basically specifies to us how much they like different types of movies. If we can get these parameters theta from our users, then it turns out that it becomes possible to try to infer what are the values of x1 and x2 for each movie. Let's look at an example. Let's look at movie 1. So that movie 1 has associated with it a feature vector x1. And this movie is called Love at Last, but let's ignore that. So let's pretend we don't know what this movie is about, right? So let's ignore the title of this movie. All we know is that Alice loved this movie, Bob loved this movie, Carol and Dave hated this movie. So what can we infer? Well, we know from the feature vectors that Alice and Bob love romantic movies because they told us that, the 5s here. Whereas Carol and Dave, we know that they hate romantic movies and that they love action movies. So, because those are the parameter vectors that users 3 and 4, Carol and Dave gave us. And so based on the fact that movie 1 is loved by Alice and Bob and hated by Carol and Dave, we might reasonably conclude that, this is probably a romantic movie. It's probably not much of an action movie. This example is a little bit mathematically simplified, but what we're really asking is what feature vector should x1 be so that theta1 transpose x1 is approximately equal to 5, that's Alice's rating, and theta2 transpose x1 is also approximately equal to 5, and theta3 transpose x1 is approximately equal to 0, so this would be Carol's rating, and theta4 transpose x1 is approximately equal to 0. And from this it looks like, x1 equals 1, that's the intercept term, and then 1.0, 0.0. That makes sense given what we know of Alice, Bob, Carol, and Dave's preferences for movies and the way they rated this movie. And so more generally, we can go down this list and try to figure out what might be reasonable features for these other movies as well. features for these other movies as well. Let's formalize this problem of learning the features xi. Let's say that our users have given us their preferences. So let's say that our users have come and told us these values for theta 1 through theta of nu, and we want to learn the feature vector xi for movie number I. What we can do is therefore pose the following optimization problem. So we want to sum over all the indices j for which we have a rating for movie I, because we're trying to learn the features for movie I, that is this feature vector xi. So, and then what we want to do is minimize this squared error. So we want to choose features xi so that the predicted value of how user j rates movie I will be similar, will be not too far in the squared error sense of the actual value yij that we actually observe in the rating of user j on movie I. So just summarize what this term does is it tries to choose features xi so that for all the users j that have rated that movie, our algorithm also predicts a value for how that user would have rated that movie that is not too far in the squared error sense from the actual value that the user had rated that movie. So that's the squared error term, and as usual we can also add this sort of regularization term to prevent the features from becoming too big. So this is how we would learn the features for one specific movie, but what we want to do is learn all the features for all the movies, and so what I'm going to do is add this extra summation here. So I'm going to sum over all nm movies, n subscript n movies, and minimize this objective on top that sums over all movies. And if you do that, you end up with the following optimization problem. And if you minimize this, you have hopefully a reasonable set of features for all of your movies. So putting everything together, the algorithm we talked about in the previous video and the algorithm that we just talked about in this video. In the previous video, what we showed was that if you have a set of movie ratings, so if you have the data, the RIJs, and if you have the YIJs, right? So you have the movie ratings. Then given features for your different movies, we can learn these parameters data. So if you knew the features, you can learn the parameters data for your different users. And what we showed earlier in this video is that if your users are willing to give you parameters, then you can estimate features for the different movies. So this is kind of a chicken and egg problem, right? Which comes first? Do we want to, if we can get the thetas, we can learn the x's. If we have the x's, we can learn the thetas. And what you can do, and then this actually works, what you can do is in fact randomly guess some value of the thetas. Now based on your initial random guess for the thetas, you can then go ahead and use the procedure that we just talked about in order to learn features for your different movies. Now, given some initial set of features for your movies, you can then use this first method that we talked about in the previous video to try to get an even better estimate for your parameters theta. Now that you have a better setting of the parameters theta for your users, you can use that to maybe get an even better set of features, and so on. You can sort of keep iterating, going back and forth, and optimizing theta, x theta, x theta, x, and this actually works. And if you do this, this will actually cause your algorithm to converge to a reasonable set of features for your movies and a reasonable set of parameters for your different users. So this is a basic collaborative filtering algorithm. This isn't actually the final algorithm that we're going to use. In the next video, we're going to be able to improve on this algorithm and make it quite a bit more computationally efficient. But hopefully this gives you a sense of how you can formulate a problem where you can simultaneously learn the parameters and simultaneously learn the features for the different movies. And for this problem, for the recommender system problem, this is possible only because each user rates multiple movies, and hopefully each movie is rated by multiple users. And so you can do this back and forth process to estimate theta on x. So to summarize, in this video we've seen an initial collaborative filtering algorithm. The term collaborative filtering refers to the observation that when you run this algorithm with a large set of users, what all of these users are effectively doing are sort of collaboratively or collaborating to get better movie ratings for everyone, because with every user rating some subset of the movies, every user
Well, there is no fuse currently. So I play max every time, average watch time 34 seconds. probably from that 5 p.m. to 10 p.m. Yeah. Well, okay. Okay, so episode 2 will be announced tomorrow. Yeah. So let's start.
In the last couple videos, we talked about the ideas of how, first, if you're given features for movies, you can use that to learn parameters data for users. And second, if you're given parameters for the users, you can use that to learn features for the movies. In this video, we're going to take those ideas and put them together to come up with a collaborative filtering algorithm. So one of the things we worked out earlier is that if you have features for the movies, then you can solve this minimization problem to find the parameters data for your users. And then we also worked out that if you are given the parameters theta, you can also use that to estimate the features x, and you can do that by solving this minimization problem. So one thing you could do is actually go back and forth, maybe randomly initialize the parameters and then solve for theta, solve for x, solve for theta, solve for x. But it turns out that there's a more efficient algorithm that doesn't need to go back and forth between the x's and the thetas, but that can solve for theta and x simultaneously. And here it is. What we're going to do is basically take both of these optimization objectives and put them into the same objective. So I'm going to define a new optimization objective, j, which is a cost function that's a function of my features x and a function of my parameters theta. And it's basically the two optimization objectives I had on top, but put together. So in order to explain this, first I want to point out that this term over here, this squared error term, is the same as this squared error term. And the summations look a little bit different, but let's see what the summations are really doing. The first summation is sum over all users j, and then sum over all movies rated by that user. Right? So this is really summing over all pairs ij that correspond to a movie that was rated by a user. It's a sum over j, says for every user, sum over all the movies rated by that user. This summation down here just does things in the opposite order. This says for every movie I, sum over all the users j that have rated that movie. And so, these summations, both of these are just summations over all pairs ij for which r of ij is equal to 1. It's just summing over, all the user movie pairs for which you have a rating. And so those two terms up there is just exactly this first term, and I've just written the summation here explicitly where I'm just saying, the sum of all pairs ij such that rij is equal to 1. And so what we're going to do is define a combined optimization objective that we want to minimize in order to solve simultaneously for x and theta. And then the other terms in the optimization objective are this, which is a regularization in terms of theta, and so that came down here. And the final piece is this term, which is my optimization objective for the x's, and that became this. And this optimization objective, j, actually has an interesting property that if you were to hold the x's constant and just minimize with respect to the thetas, then you'd be solving exactly this problem. Whereas if you were to do the opposite, if you were to hold the thetas constant and minimize j only with respect to the x's, then it becomes equivalent to this, because either this term or this term is constant if you're minimizing only with respect to the x's or only with respect to the thetas. So here's an optimization objective that puts together my cost functions in terms of x and in terms of theta. And in order to come up with what's just one optimization problem, what we're going to do is treat this cost function as a function of my features x and of my per user parameters theta, and just minimize this whole thing as a function of both the x's and a function of the thetas. And really, the only difference between this and the older algorithm is that instead of going back and forth, previously we talked about minimizing with respect to theta, then minimizing with respect to x, minimizing with respect to theta, minimizing with respect to x, and so on. In this new version, instead of sequentially going between the two sets of parameters x and theta, what we're going to do is just minimize with respect to both sets of parameters simultaneously. Finally, one last detail is that when we're learning the features this way, previously we have been using this convention that we have a feature x0 equals 1 that corresponds to an intercept term. When we're using this sort of formalism where we're actually learning the features, we're actually going to do away with this convention, and so the features we're going to learn x will be in Rn, right? Whereas previously we had features x in Rn plus 1, including the intercept term. By getting rid of x0, we now have just x in Rn. And so similarly, because the parameters theta is in the same dimension, we now also have theta in Rn, because if there's no x0, then there's no need for a parameter theta 0 as well. And the reason we do away with this convention is because we're now learning all the features, right? So that just means that there's no need to hard code a feature that's always equal to 1, because if the algorithm really wants a feature that's always equal to 1, it can choose to learn one for itself. So if the algorithm chooses, it can set the feature x1 equals to 1, and so there's no need to hard code the feature that's always equal to 1. The algorithm now has the flexibility to just learn it for itself. So putting everything together, here's our collaborative filtering algorithm. First, we're going to initialize x and theta to small random values. And this is a little bit like neural network training, where there we were also initializing all the parameters of the neural network to small random values. Next, we're then going to minimize the cost function using gradient descent, or one of the advanced optimization algorithms. So if you take derivatives, you find that the gradient descent updates are like these. And so this term here is the partial derivative of the cost function. I'm not going to write that out with respect to the feature value xik, and similarly, this term here is also a partial derivative value of the cost function with respect to the parameter theta that we're minimizing. And just as a reminder, in this formalism, we no longer have this x0 equals 1, and so we have that x is in Rn and theta is in Rn. And in this new formalism, we're regularizing every one of our parameters theta and every one of our parameters x, and there's no longer this special case theta 0, which was regularized differently, or which was not regularized compared to the parameters theta 1 down to theta. Okay, so there's now no longer a theta 0, which is why in these updates I did not break out the special case for k equals 0. So we then use gradient descent to minimize the cost function j with respect to the features x and with respect to the parameters theta. And finally, given a user, if a user has some parameters theta, and if there's a movie with some sort of learned features x, we would then predict that that movie will be given a star rating by that user of theta transpose j. Or just to fill this in, we're saying that if user j has not yet rated movie I, then what we do is predict that user j is going to rate movie I according to this. So theta j transpose xi. So that's the collaborative filtering algorithm, and if you implement it, so theta j transpose. In the last few videos, we talked about a collaborative filtering algorithm. In this video, I want to say a little bit about the vectorization implementation of this algorithm, and also talk a little bit about other things you can do with this algorithm. For example, one of the things you can do is, given one product, can you find other products that are related to this? So that if, for example, a user has recently been looking at one product, are there other related products that you could recommend to this user? So let's see what we can do about that. What I'd like to do is work out an alternative way of writing out the predictions of the collaborative filtering algorithm. To start, here's our data set with our 5 movies, and what I'm going to do is take all the ratings by all the users and group them into a matrix. So here we have 5 movies and 4 users, and so this matrix Y is going to be a 5 by 4 matrix. It's just taking all the elements, all of this data, including question marks, and grouping them into this matrix. And of course, the elements of this matrix, or the ij element of this matrix, is really what we were previously writing as Y superscript I comma j. It's the rating given to movie I by user j. Given this matrix Y of all the ratings that we have, there's an alternative way of writing out all the predicted ratings of the algorithm. And in particular, if you look at what a certain user predicts on a certain movie, what user J predicts on movie I is given by this formula. And so if you have a matrix of the predicted ratings, what you would have is the following matrix, where the I comma j entry, so this corresponds to the rating that we predict user J will give to movie I, is exactly equal to that theta j transpose xi. And so this is a matrix where this first element, the 1 1 element, is the predicted rating of user 1 on movie 1, and this element, this is the 1 2 element, is the predicted rating of user 2 on movie 1, and so on. And this is the predicted rating of user 1 on the last movie. And if you want, this rating is what we would have predicted for this value, and this rating is what we would have predicted for that value, and so on. Now, given this matrix of predicted ratings, there is then a simpler or vectorized way of writing this out. In particular, if I define a matrix X, and this is going to be just like the matrix we had earlier for linear regression to be sort of x1 transpose, x2 transpose, down to x of nm transpose. So I'm going to take all the features for my movies and stack them in rows. So if you think of each movie as one example and stack all of the features for the different movies in rows, and if we also define a matrix capital theta, and what I'm going to do is take each of the per user parameter vectors and stack them in rows like so. So that's theta 1, which is the parameter vector for the first user, and here's theta 2, and so I'm going to stack them in rows like this to define a matrix capital theta, and so I have n u parameter vectors all stacked in rows like this. Now, given this definition for the matrix X and this definition for the matrix theta, in order to have a vectorized way of computing the matrix of all of the predictions, you can just compute X times the matrix theta transpose, and that gives you a vectorized way of computing this matrix over here. To give the collaborative filtering algorithm that we've been using another name, the algorithm that we're using is also called low rank matrix factorization. And so if you hear people talk about low-rank matrix factorization, that's essentially exactly the algorithm that we've been talking about. And this term comes from the property that this matrix, X times theta transpose, has a mathematical property in linear algebra called that this is a low-rank matrix. And so that's what gives rise to this name, low-rank matrix factorization for these algorithms, because of this low-rank property of this matrix X theta transpose. In case you don't know what low rank means, or in case you don't know what a low rank matrix is, don't worry about it. You really don't need to know that in order to use this algorithm. But if you're an expert in linear algebra, that's what gives this algorithm this other name of low rank matrix factorization. Finally, having run the collaborative filtering algorithm, here's something else that you can do, which is use the learned features in order to find related movies. Specifically, for each product I, really for each movie I, we've learned a feature vector xi. So, when you learn a set of features, you don't really know in advance what the different features are going to be. But if you run the algorithm empirically, the features will tend to capture what are the important aspects of these different movies or different products or what have you. What are the important aspects that cause some users to like certain movies and cause some users to like different sets of movies. And so maybe you end up learning a feature, where x1 equals romance, x2 equals action, similar to an earlier video, and maybe you learn a different feature, x3, which is the degree to which this is a comedy, learn some feature x4, which is, some other thing. And you have n features altogether, and after you've learned features, it's actually often pretty difficult to go into the learned features and come up with a human understandable interpretation of what these features really are. But in practice, the features, even though these features can be hard to visualize, can be hard to figure out just what these features are, usually it will learn features that are very meaningful for capturing whatever are the most important or the most salient properties of a movie that causes users to like or dislike it. And so now, let's say we want to add just the following problem. Say you have some specific movie I, and you want to find other movies J that are related to that movie. And so, well, why would you want to do this, right? Maybe you have a user that's browsing movies and they're currently watching movie J. Then what's a reasonable movie to recommend to them to watch after they're done with movie J? Or if someone's recently purchased movie J, well, what's a different movie that would be reasonable to recommend to them for them to consider purchasing? So now that we've learned these feature vectors, this gives us a very convenient way to measure how similar two movies are. In particular, movie I has a feature vector xi, and so if you can find a different movie J so that the distance between xi and xj is small, then this is a pretty strong indication that, you know, movies j and I are somehow similar, at least in the sense that someone that likes movie I may be more likely to like movie j as well. So just to recap, if your user is looking at some movie I, and if you want to find the 5 most similar movies to that movie in order to recommend 5 new movies to them, what you do is find the 5 movies j with the smallest distance between the features between these different movies. And this could give you a few different movies to recommend to your user. So with that, hopefully you now know how to... By now you've seen all of the main pieces of the recommender system algorithm, or the collaborative filtering algorithm. In this video, I want to just share one last implementational detail, namely mean normalization, which can sometimes just make the algorithm work a little bit better. To motivate the idea of mean normalization, let's consider an example of where there's a user that has not rated any movies. So in addition to our 4 users, Alice, Bob, Carol, and Dave, I've added a 5th user, Eve, who hasn't rated any movies. Let's see what our collaborative filtering algorithm will do on this user. Let's say that n is equal to 2, and so we're going to learn 2 features, and we're going to have to learn a parameter vector theta 5, which is going to be in R2. Remember, this is now vectors in Rn, not Rn plus 1. We're going to learn the parameter vector theta 5 for our user number 5, Eve. So if we look in the first term in this optimization objective, well, the user Eve hasn't rated any movies, and so, you know, there are no movies for which Rij is equal to 1 for the user Eve, and so this first term plays no role at all in determining theta 5, because there are no movies that Eve has rated. And so the only term that affects theta 5 is this term. And so we're saying that we want to choose vector theta 5 so that the last regularization term is as small as possible. In other words, we want to minimize this lambda over 2 theta 5 subscript 1 squared plus theta 5 subscript 2 squared. So that's the component of the regularization term that corresponds to user 5. And of course, if your goal is to minimize this term, then what you're going to end up with is just theta 5 equals 0, 0, because the regularization term is encouraging us to set parameters close to 0, and if there is no data to try to pull the parameters away from 0, because this first term it doesn't affect theta 5, we just end up with theta 5 equals the vector of all zeros. And so when we go to predict how user 5 will rate any movie, we have that theta 5 transpose xi for any I, that's just going to be equal to 0. Right? So because theta 5 is 0, for any value of x, this inner product is going to be equal to 0. And what we're going to have, therefore, is that we're going to predict that Eve is going to rate every single movie with 0 stars. But this doesn't seem very useful, does it? I mean, if you look at the different movies, you know, Love at Last, this first movie, a couple people rated it 5 stars, and for, you know, even the Swords versus Karate, someone rated it 5 stars. So some people do like some movies. It seems kind of not useful to just predict that Eve is going to rate everything 0 stars. And in fact, if we're predicting that Eve is going to rate everything 0 stars, we also don't have any good way of recommending any movies to her, because, you know, all of these movies are getting exactly the same predicted rating for Eve, so there's no one movie with a higher predicted rating that we could recommend to her. So that's not very good. The idea of mean normalization will let us fix this problem. So here's how it works. As before, let me group all of my movie ratings into this matrix Y. So just take all of these ratings and group them into this matrix Y. And this column over here of all question marks corresponds to Eve's not having rated any movies. Now, to perform mean normalization, what I'm going to do is compute the average rating that each movie obtained. And I'm going to store that in a vector that we call mu. So the first movie got 2 5-star and 2 0-star ratings, so the average of that is a 2.5 star rating. The second movie had an average of 2.5 star, and so on. And the final movie has 0050, and the average of 0050, that averages out to an average of 1.25 rating. And then what I'm going to do is look at all the movie ratings, and I'm going to subtract off the mean ratings. So this first element 5, I'm going to subtract off a 2.5, and that gives me 2.5. And the second element 5, subtract off a 2.5, get a 2.5. And then these 0 zeros, subtract off 2.5, and get minus 2.5, minus 2.5. In other words, what I'm going to do is take my matrix of movie ratings, take this Y matrix, and subtract from each row the average rating for that movie. So what I'm doing is I'm just normalizing each movie to have an average rating of 0. And so just one last example, if you look at this last row, the 0050, we're going to subtract 1.25, and so it ends up with these values over here. Okay, so now, and of course the question marks stay a question mark. 0, we're going to subtract 1.25, and so it ends up with these values over here. Okay, so now, and of course the question marks stay a question mark. And so each movie in this new matrix Y has an average rating of 0. What I'm going to do then is take this set of ratings and use it with my collaborative filtering algorithm. So I'm going to pretend that this was the data that I had gotten from my users. I'm going to pretend that these were the actual ratings I had gotten from the users, and I'm going to use this as my data set with which to learn my parameters theta j and my features xi from these mean normalized movie ratings. When I want to make predictions of movie ratings, what I'm going to do is the following. For a user j on movie I, I'm going to predict theta j transpose xi, where x and theta are the with which to learn this y. This first element 5, I'm going to subtract off a 2.5, and that gives me a 2.5. And the second element 5, subtract off a 2.5, get a 2.5. And then these 0 zeros, subtract off 2.5, and get minus 2.5, minus 2.5. In other words, what I'm going to do is take my matrix of movie ratings, take this Y matrix, and subtract from each row the average rating for that movie. So what I'm doing is I'm just normalizing each movie to have an average rating of 0. And so just one last example, if you look at this last row, the 0050, we're going to subtract 1.25, and so it ends up with these values over here. Okay, so now, and of course the question marks stay a question mark. And so each movie in this new matrix Y has an average rating of 0. What I'm going to do then is take this set of ratings and use it with my collaborative filtering algorithm. So I'm going to pretend that this was the data that I had gotten from my users. I'm going to pretend that these were the actual ratings I had gotten from the users, and I'm going to use this as my data set with which to learn my parameters theta j and my features xi from these mean normalized movie ratings. When I want to make predictions of movie ratings, what I'm going to do is the following. For a user j on movie I, I'm going to predict theta j transpose xi, where x and theta are the parameters I've learned from this mean normalized data set. But because on the data set I had subtracted off the means, in order to make a prediction on movie I, I'm going to need to add back in the mean, and so I'm going to add back in mu I, and so that's going to be my prediction, where in my training data I subtracted off all the means, and so when I make predictions I need to add back in these means mu I for movie I. And so specifically for user 5, which is Eve, the same argument as the previous slide still applies, in the sense that Eve had not rated any movies, and so the learn parameter for user 5 is still going to be equal to 0, 0. So what we're going to get then is that on a particular movie I, we're going to predict for Eve theta 5 transpose xi plus add back in mu I. And so this first component is going to be equal to 0 if theta 5 is equal to 0. And so on movie I, we're going to end up predicting mu I. And this actually makes sense. It means that on movie 1, we're going to predict Eve rates at 2.5. On movie 2, we're going to predict Eve rates at 2.5. On movie 3, we're going to predict Eve rates at 2, and so on. And this actually makes sense because it says that if Eve hasn't rated any movies, we just don't know anything about this new user Eve, what we're going to do is just predict for each of the movies whatever the average rating that those movies got. Finally, as an aside, in this video we talked about mean normalization, where we normalize each row of the matrix Y to have mean 0. In case you have some movies with no rating, so this is analogous to a user who hasn't rated anything, but in case you have some movies with no ratings, you can also play with versions of the algorithm where you normalize the different columns to have mean 0 instead of normalizing the rows to have mean 0. Although that's maybe less important because if you really have a movie with no ratings, maybe you just shouldn't recommend that movie to anyone anyway. And so taking care of the case of a user who hasn't rated anything might be more important than taking care of the case of a movie that hasn't gotten a single rating. So to summarize, that's how you can do mean normalization as a sort of pre-processing step for collaborative filtering. Depending on your data set, this might sometimes make your implementation work just a little bit better.
So previously, I accidentally did not, what is it? Uncheck the break time. So when I was studying the material, I forgot to click the check button for the break time. So it wasn't a break. It wasn't a break time. It was a studying time. I think I left it check for like 30 minutes or something. Yeah. I guess this is the end of the stream. I guess 4 hours and yeah, 4 hours studying with me. Yeah. Okay, see you next time. Maybe tomorrow. Tomorrow will be a episode 2. Episode 2, study with me. Okay. Bye.